Out there, the universe has built things so enormous they blur the line between object and the cosmos itself. Structures so vast they shouldn't exist at all, yet they're written across the sky like scars. If these giants are real, what breaks first? Our maps of the universe, our theories of how matter clumps, or the idea that the cosmos has any limit? Scale is the universe's oldest weapon, quiet, patient, and capable of turning certainty into vertigo. Tonight we follow that weapon outward, until numbers become landscapes and distance becomes doubt. To understand the largest things, we first have to admit a dangerous truth. Size is not a single fact. It is a negotiation between light and time, between definitions and data, between what a telescope can see and what gravity can hold. Across the sky, our instruments do not photograph the cosmos as it is, but as it was. Each farther step also steps deeper into history. A cluster's heat, a galaxy's faint halo, a quasar's flare, a burst of gamma rays. Each is a different kind of ruler, and each can mislead. That is why this journey is not a parade of superlatives, but an investigation into how the universe builds structure at all. We will ask where the cosmic web truly ends, why some regions gather into empires of galaxies, and how a single black hole can outweigh intuition while still hiding inside a point. Along the way, we will meet giants that look solid and giants that look statistical. Patterns that may be real architecture or the echo of how we search. Some claims will feel like a violation of the cosmological principle, others like a lesson in humility, and a few like a warning that our maps are only as honest as their methods. Because at the farthest limit, the ultimate colossus is not a wall of matter, but a boundary of information, an edge drawn by the finite speed of light. And when the universe is measured by horizons instead of landmarks, the question changes from how big is it to what can ever be known. This is not a story about bigger and bigger objects for their own sake. It is a story about the rare extremes that stress test a mostly uniform cosmos, and about the thin line between discovery and mirage when we name something too large to hold in the mind. Before we begin, let us know in the comments below where in the world you're watching from and what time it is there. Now, settle in for a journey. We begin by learning to measure the unthinkable, then climb from our home supercluster to remote knots, controversial walls, and record-breaking galaxies. Finally, we reach the only edge that matters, and discover what that limit demands of every claim before it. Size is the first trap in cosmology, because our instincts evolved for hills and horizons. Our brains are excellent at judging what a body can cross in an afternoon, yet they were never trained on light itself. The universe does not scale in steps we can feel. It scales in powers of 10, and it punishes casual comparisons, especially the kind that sound reasonable in ordinary speech. Start close, where the numbers still feel like geography. Earth and the Moon look like neighbours in the sky, a paired system you could almost imagine reaching. Yet light needs more than a second to cross that gap, and radio signals inherit the same delay. In a visual, the Moon hangs like a bright coin above a dark ocean, while a thin beam traces the invisible time it takes to arrive. Stretch outward to the Sun, and the same light takes about 8 minutes. That delay is not trivia. It means every sunrise is a message from the past, and every solar flare is observed after it has already happened. In footage, the Sun's surface boils with granulation, and the clock in the corner quietly reminds us we are watching history. Keep going to the edge of the solar system, and even familiar spacecraft drift for years. The heliosphere thins into a region where the solar wind yields to interstellar gas, and distances stop behaving like road trips. A probe becomes a moving pixel against a black field, and the emptiness between objects becomes the dominant feature. The reset is not only about distance, it is about how little there is to hold onto between islands of matter. Then the reset becomes brutal. The nearest star is more than 4 light-years away, and that is still our front yard. In that span, the solar system would shrink to a speck, and the space between stars would feel like an ocean without shores. A light-year is not a unit of time here. It is distance defined by how far light travels in 1 year, about 9.46 trillion kilometers, a number that resists intuition. The mind fails because distance grows exponentially, while our mental map grows linearly. We picture a bigger room, then a bigger city, then a bigger country, and we expect the same ladder to keep working. Space does not cooperate with that ladder. It jumps from planets to starfields to galaxies with no middle scale that feels natural. And the jumps arrive faster than our metaphors can adapt. A galaxy is the next true unit of place, because it is a long-lived gravitational system. The Milky Way spans roughly 100,000 light-years, and that number is already hard to hold without a diagram. It contains hundreds of billions of stars plus gas, dust and dark matter that outweighs the luminous parts. Our solar system is not near the centre and not near the edge. It is simply embedded in one spiral arm among many, orbiting the galactic centre over hundreds of millions of years. In visuals, the Milky Way becomes a luminous disk with dark lanes of dust, and the camera pulls back until the Sun's orbit is a faint ring. Star-forming regions glow pink in hydrogen light, while older stars fill the bulge with warm yellow. Even here, where we are is a statistical statement. We live inside a rotating pattern of stars, gas clouds, and invisible mass that shapes the whole structure. Beyond the Milky Way sits the local group, a small association of galaxies bound by gravity. Andromeda and the Milky Way dominate it, with dozens of smaller companions that orbit like moths around porchlights. The local group is not the universe's basic building block. It is one bead on a much larger web, and its boundaries blur into the surrounding field of galaxies. Step again. Galaxies gather into groups, groups into clusters, and clusters into superclusters. Between them lie voids, regions with far fewer galaxies than average, where the darkness is not empty but underpopulated. The pattern is not random. It resembles a cosmic foam, shaped by gravity acting on early ripples, and amplified as matter falls into dense regions over billions of years. Those ripples have a history, and it matters. In the early universe, tiny fluctuations in density were imprinted and then stretched to cosmic scales, later becoming the seeds of galaxies and clusters. Inflation is one proposed mechanism for that imprint, and cold dark matter helps those seeds grow without being erased by radiation pressure. When we map the web today, we are reading a fossil record of those initial conditions. To talk about these scales, we need a measurement toolkit that stays stable when intuition collapses. The first tool is the light year, useful because it ties distance to a constant speed, and because it translates directly into travel time for a photon. The second is the parsec, built from geometry rather than travel time, and it is the unit that quietly runs modern astronomy. A parsec comes from parallax, the apparent shift of a nearby star against distant background stars. As Earth moves around the Sun, nearby stars seem to wobble relative to the far field, and that wobble can be measured as an angle. 1 parsec is the distance at which one astronomical unit subtends 1 arcsecond. It equals about 326 light-years, and astronomers often speak in kiloparsecs and megaparsecs because the equations stay readable. Historically, parallax was a turning point. For centuries, the lack of measurable stellar parallax was used as an argument against Earth's motion, until instruments became precise enough to detect the tiny shifts. Once parallax was measured, the stars stopped being a painted dome and became a 3-dimensional neighbourhood. In a graphic, the triangle from Earth's orbit to a star is thin as a hair, yet it anchors the entire distance ladder. Distance alone is not enough, because the universe expands while light is in transit. Expansion stretches the wavelength of light, shifting it toward red, and the spectrum becomes a ruler etched with atomic fingerprints. That shift is redshift, written as Z. Redshift is not just a Doppler effect from motion through space. It is also the stretching of space itself, which lengthens the light wave as it travels. Redshift becomes a kind of cosmic ruler. For nearby galaxies, Z correlates with distance through Hubble's law, and the relationship is close to linear. For distant galaxies, the relationship depends on the universe's expansion history, which is not constant over time. That history is encoded in cosmological parameters, including dark energy and matter density, and it is tested by how brightness, size, and redshift fit together. Look-back time is the next concept, and it is where scale becomes unsettling. When we observe a galaxy at high redshift, we see it as it was, not as it is now, because the light left long ago. The universe has changed since then, and galaxies themselves evolve through mergers, star formation, and feedback from black holes. Distance becomes tied to time, and every deep image is also an archaeological layer, older the farther you look. Now the definitions fork and language starts to wobble. Proper distance is the separation between 2 points at a given cosmic time, like measuring with a ruler laid down right now. Comoving distance factors out expansion, keeping coordinates fixed with the Hubble flow, so the grid expands while the coordinates stay put. Both are valid, and both can be called distance depending on the question you're asking. That is why the same object can have multiple sizes. A structure can be measured by its extent in proper distance today, which tells you how big it is in the present universe. It can be measured by its comoving size, which tracks the scale of the initial perturbation that grew into it. It can be measured by the light travel distance, which is not the same thing at all, because the universe expanded during the journey. Even the word size needs a definition. Is it the diameter of a cluster's virialized core, where gravity has settled the system into a quasi-equilibrium? Is it the full region of infall, where galaxies are still streaming inward along filaments? Is it a statistical boundary drawn from density thresholds in a survey, where the contour depends on the chosen cutoff? Each choice changes the headline number, and each headline number carries hidden assumptions. So how do we actually map the large-scale universe when we cannot step outside it? We do it by collecting many faint points of light, then turning them into a three-dimensional catalogue through careful inference. Galaxy redshift surveys measure positions on the sky and redshifts along the line of sight, and they do it for millions of galaxies at once. With enough galaxies, the cosmic web emerges as a measurable pattern, with filaments, nodes, and voids that can be quantified. In visuals, the survey becomes a wedge of space filled with glowing dots, then a rotating lattice as the camera flies through. Dense knots mark clusters, and long strands trace filaments that look almost biological. Yet the beauty hides a warning. Every dot is filtered through instrument sensitivity, exposure time, and how the survey chooses its targets. Surveys also reveal a danger. A thin slice through space can make separate structures look connected, because projection compresses depth into a single plane. A sparse sample can turn noise into apparent walls, especially when algorithms link points into chains. Selection effects can imprint patterns that are not truly there, because brighter galaxies are overrepresented at large distances. The bigger the claim, the more the measurement details matter, down to calibration, completeness, and error bars. We add other tracers to reduce ambiguity because light alone can mislead. Gravitational lensing maps mass directly, including dark matter, by measuring subtle distortions in background galaxies. The effect is small, often a percent-level stretch, so it requires averaging over many sources. Lensing does not care whether matter shines. It cares only about gravity, and it reveals where the mass really sits. X-ray observations map hot gas in clusters, where temperatures reach tens of millions of degrees. That gas emits X-rays through thermal processes, and it fills the space between galaxies like a thin, glowing atmosphere. The gas traces deep gravitational wells and helps define cluster boundaries in a physically meaningful way. It also reveals mergers, shocks, and the violent growth of structure, where two clusters collide and the gas lags behind the dark matter. Radio observations expose jets from active galaxies, which can extend far beyond their host galaxies. These jets are launched near supermassive black holes, where magnetic fields and accretion disks convert gravity into collimated beams. They carve through intergalactic space and light up magnetic fields, producing lobes that can dwarf the visible galaxy. They are not the biggest structures by volume, but they are among the longest coherent objects we can see, like intergalactic lightning frozen in slow motion. Transient beacons add another layer, because they can be seen when ordinary galaxies are too faint. Gamma-ray bursts can be detected across much of the observable universe, briefly outshining entire galaxies in high-energy light. Their afterglows provide redshifts and pinpoint distant star-forming regions, anchoring points in otherwise hard-to-map territory. They can also be used cautiously to test whether matter is clumped more than expected on huge scales, though the statistics are delicate. All these methods are attempts to answer a single question. What is the largest coherent structure the universe can build? The standard model of cosmology, with inflation and cold dark matter, predicts a universe that becomes more uniform at the larger scales. Structure grows from small seeds, but the growth is limited by expansion and by the finite time available since the Big Bang. This expectation is captured by the cosmological principle. On sufficiently large scales, the universe should look statistically the same in every direction and from every location, even if it is lumpy up close. It does not claim perfect smoothness, and it does not deny clusters or voids. It claims that the lumps average out when you zoom far enough out, and that no special direction or location is privileged. There is also a related idea called the end of greatness. It suggests there is a scale beyond which structure stops growing in a meaningful way because the density field approaches homogeneity. Below that scale, clusters and filaments stand out as distinct features. Above it, the distribution becomes smoother, and apparent patterns should be mostly statistical, products of chance alignments in a finite sample. The mystery begins when observations flirt with that boundary. Surveys have reported walls, arcs, and supercluster complexes that seem too extended to be typical, especially when drawn as continuous features. Some appear to span billions of light-years in co-moving terms, which is where the discomfort starts. If they are real as single connected entities, they challenge how quickly the universe should smooth out, and they pressure test the assumptions behind our models. But the word real is slippery here, and cosmology is careful with it. A structure can be real as a statistical overdensity, yet not a bound object that will remain together. It can be real as a chain of correlated regions, yet not a single coherent thing with a shared fate. It can also be an artifact of how we draw contours through sparse data, where the contouring method becomes part of the claim. Cosmology lives in that tension between map and territory. We infer three-dimensional structure from two-dimensional sky positions and redshifts, and we do it while the universe itself is expanding. We correct for peculiar velocities, survey geometry, and dust that dims and reddens light in our own galaxy. We choose algorithms that connect points into filaments, and those choices can create or erase giants, sometimes without anyone noticing at first. If the giants are mirages, the lesson is about humility in measurement, and about how easily pattern-seeking minds can be fooled. If the giants are real, the lesson is about physics, and about whether our parameters or assumptions need revision. Either way, the stakes are high, because the larger structures test the assumptions that make the rest of cosmology work. They are not just curiosities, they are stress tests. This is why size matters beyond spectacle. The growth of structure is governed by gravity, dark matter, and the expansion rate, and those ingredients interact over cosmic time. Change any of those, and the maximum coherent scale shifts, along with the expected statistics of walls and voids. The biggest objects become a diagnostic of the universe's ingredients and its history, like a fingerprint left on the sky. We also need to be careful about what we mean by object. A planet is an object because it is bound and distinct, with a clear edge defined by its own gravity. A galaxy is an object because it holds together over time, even as it accretes and merges. A supercluster may be an address rather than a thing, a region where flows converge but binding is incomplete, and where the future may be dispersal rather than collapse. That ambiguity is not a flaw in storytelling, it is the central puzzle, and it is why the larger scales feel uncanny. The universe may not divide neatly into objects at the larger scales. It may instead present gradients, networks, and statistical fields that only look like discrete entities when we force them into categories. When we label a wall, we're also declaring what counts as connected. Still, some names keep returning because they organize the map and guide the questions. Laniakea is one of them, a vast basin of attraction that includes the Milky Way and many neighboring groups. It is defined by galaxy motions and the direction of gravitational flow, not by a bright boundary you can photograph. It is less a wall than a watershed in the cosmic web, an answer to the question, which way does matter tend to fall? Superclusters are the next rung, sometimes described like empires of galaxies. They are not necessarily bound, but they trace the densest parts of the web where filaments intersect. Their shapes depend on how we define membership, and their sizes depend on whether we use co-moving or proper distance. In wide-field imagery, they appear as crowded regions where the sky seems to thicken with galaxies. Then there are radio galaxies, whose jets can stretch for millions of light-years, maintaining direction across astonishing emptiness. They are not the biggest by mass, but their linear extent is shocking, and their symmetry hints at stable central engines. They show that coherent structures can persist across intergalactic space, guided by black holes and magnetic fields, and shaped by the medium they plough through. And beyond those lies the category that causes the most unease: great walls and enormous associations, reported in galaxy surveys and in GRB distributions, where the scale itself becomes the headline. The Hercules Corona Borealis Great Wall is often cited as a potential record breaker, with a claimed scale so large it strains the end of greatness. In a visualization, it appears as a broad arc of points, like a faint continent traced in starlight. The claim is controversial for good reasons. The data are sparse, the selection effects are complex, and the definition of connectedness is debatable, especially when the structure is inferred from a limited set of beacons. Yet the claim persists, because it sits exactly where our expectations become fragile. It forces us to ask whether we are seeing structure, coincidence, or a hint of missing physics, an uncomfortable question that keeps returning. So Chapter 1 is a calibration, and calibration is not glamorous, but it is essential. We have reset the scale from the Moon to the Milky Way, then out to the cosmic web, where even the word nearby becomes technical. We have assembled the tools, light years and parsecs, redshift and look-back time, co-moving and proper distance. We have also admitted that size depends on definitions, and definitions can mislead, especially when the data are thin. Now the documentary's central question comes into focus. How can the universe build structures on scales that seem to defy our models? Are the largest objects genuine coherent entities, statistical mirages amplified by our methods, or signs that our cosmological assumptions are incomplete? And if the answer changes with the definition of size, what does that say about the way we carve reality into categories? The next step is to leave the abstract toolkit and enter specific territory. We will start with our own cosmic address, then climb outward through ever larger claims, watching the web sharpen and then blur again. Each chapter will test what we mean by object, and how close the universe comes to breaking its own rules. Chapter 1 built the measuring tools and warned that size depends on definitions, and Chapter 2 uses a nearby giant to show how definitions can be physical, not merely visual. We are going to name a structure that cannot be circled with a pen on a photograph. We will define it the way nature defines it, through motion, through gravity, and through the subtle drift of galaxies across cosmic time. We start with a familiar claim, but we let it land with weight. The Milky Way is not floating alone in darkness, isolated like a lantern in an empty sea. It sits inside a larger association of galaxies, and that association sits inside something larger again, nested like patterns within patterns. On wide-field surveys, the sky becomes a tapestry of points, and the points become threads. Those threads gather into knots, and the knots gather into regions that feel, at first glance, like continents. Astronomers once spoke of the local supercluster, centered loosely on Virgo, because Virgo is the nearest rich cluster, and it dominates the nearby map. That name implied a visible concentration, like a city on a map, with a downtown and a fading edge. It also implied borders that could be traced by counting galaxies, then deciding where the counts dropped below some threshold. In the mid and late 20th century, as redshift surveys grew, such naming was practical. It was also tempting, because the eye loves boundaries even when nature prefers gradients. But superclusters are not like planets or galaxies, and that difference matters. They are not neatly bound objects with stable edges, and they do not rotate as coherent units. At these scales, the universe offers gradients, streams, and basins shaped by gravity, and those shapes can be shallow. Density can fade slowly, and filaments can connect regions that are not truly part of the same dynamical system. If you only look at brightness and crowding, the cosmic web can trick you into drawing walls where there are only bridges. Laniakea is the modern attempt to name our basin, and the name itself signals ambition. The word means immense heaven, drawn from Hawaiian, and the scale earns it. It is a supercluster region defined by motion, not by walls, and that choice changes what the word belongs means. Laniakea is not a single cluster, and it is not a single filament. It is a network of groups and clusters connected by filaments, with membership assigned by how galaxies move through the expanding universe. This is the key shift in Chapter 2. Instead of drawing boundaries where the galaxy density looks high, astronomers draw boundaries where the flow of galaxies changes direction. To understand that move, we need two velocities at once, and we need to keep them conceptually separate. There is the Hubble flow, the smooth recession from cosmic expansion, which is the dominant trend on large scales. And there is peculiar velocity, the extra motion caused by local gravity, layered on top of expansion like a crosswind. In everyday language, one is the overall stretching of space, and the other is the local tug of nearby mass. Hubble flow is the baseline that makes the universe readable. On average, distant galaxies recede faster, and redshift tracks that trend with remarkable regularity. The farther a galaxy is, the more its light is stretched toward longer wavelengths, and the more its spectrum slides toward red. If expansion were the only effect, every galaxy would ride the same outward current. The map would be simple, and distance would be almost interchangeable with redshift. Peculiar velocity is the deviation from that current, and it is where the story becomes textured. A galaxy can be pulled toward a mass concentration even while the overall space between them expands. The observed redshift mixes both effects, and the mix is not always obvious. A galaxy can be receding overall, yet still falling inward relative to its neighbours, because the fabric of space is stretching while gravity is pulling. That dual motion is counterintuitive, but it is the normal state of the cosmic web. For nearby galaxies, peculiar velocities are not small corrections, and that is why the local universe is both messy and informative. They can be hundreds of kilometers per second, sometimes comparable to the Hubble recession at tens of megaparsecs. A few hundred kilometers per second does not sound like much next to the speed of light, yet it is enough to distort a local map. It can make a galaxy appear farther or closer than it truly is if you rely on redshift alone. The result is that the nearby universe cannot be charted like a simple expanding balloon. Tricky, because redshift is no longer a clean distance measure nearby, and the errors are not random in direction. Revealing, because the deviations point toward hidden mass, and the patterns can be coherent across vast regions. The universe leaves fingerprints in the residuals, and those fingerprints are gravitational. When many galaxies share a drift in the same direction, it is not a coincidence. It is a clue that the landscape beneath the visible matter has a slope. So how do you measure peculiar velocities with any confidence when the signal is subtle and the distances are hard? You estimate a galaxy's true distance using standard candles or scaling relations, then compare expected Hubble recession to the observed redshift. The difference becomes a velocity, a signed quantity that can point toward or away from us. The method sounds straightforward, but each step is a careful compromise between precision and reach. Standard candles are objects whose intrinsic luminosity is known or can be calibrated, so their apparent brightness reveals distance. Cepheid variables, with their period luminosity relation, helped build the first rungs of the distance ladder. Type Ia supernovae, with their standardized peak brightness, extend that ladder far beyond the local group. Scaling relations do similar work for galaxies themselves. The Tully Fisher relation links a spiral galaxy's rotation speed to its luminosity, while the fundamental plane ties elliptical galaxy sizes, brightnesses, and velocity dispersions together. Distance indicators are imperfect, and the uncertainties are not small. Dusk and dim light, stellar populations can vary, and measurement errors accumulate with each rung of the ladder. Yet they can be combined across many galaxies, and that is where the power emerges. The noise averages down, and coherent patterns remain, especially when the sample covers the sky. Those patterns are the flow lines of the local universe, and they can be treated like a field rather than a scatterplot. In 2014, researchers used a large peculiar velocity catalogue to map these flows, building on decades of distance work. They reconstructed a velocity field, then traced streamlines like water moving across a landscape. In visual terms, arrows become currents, and currents become rivers. Where the arrows converge, the flow sinks into a basin. Where the arrows diverge, the flow splits like water at a ridge. The result was Laniakea, not as a bright blob, but as a dynamical region. A basin of attraction is the central concept, and it deserves a slower look. It is a region where flow lines converge toward a common gravitational destination, defined by the shape of the gravitational potential. In a simple picture, matter rolls downhill toward lower potential energy, although the hill is invisible. The boundary is a watershed, where flow lines diverge toward different attractors. If you stand on that watershed, a small step in one direction sends you toward one basin, and a step the other way sends you elsewhere. This is why Laniakea's border is gravitational rather than visual, and why it can feel almost philosophical. You cannot photograph a wall around it, because the border is not a ridge of galaxies. It is a change in the direction of motion, a turning of vectors in a field. In a density map, the boundary might cut through regions that still look connected. In a flow map, that same region splits cleanly, because the galaxies are headed to different destinations. The method also explains why superclusters can overlap in density space, and why older names can be both useful and misleading. Two regions can look connected in a galaxy map, yet belong to different basins. Motion separates what projection and density can confuse, especially when filaments cross the line of sight. The sky compresses 3 dimensions into 2, and the eye fills gaps with imagined continuity. Dynamics, by contrast, is harder to fool, because it encodes what gravity has been doing for billions of years. Place the Milky Way inside this picture, and the abstract becomes personal. We live in the local group, dominated by the Milky Way and Andromeda, with dozens of dwarf galaxies orbiting in their gravitational reach. The local group is not a grand metropolis of galaxies. It is a small neighbourhood, a modest knot in a much larger mesh. Yet even here, motion tells a story. Andromeda is approaching us, not receding, because local gravity overwhelms expansion at this scale. The local group sits on the outskirts of the Virgo cluster region, not at the centre, and that offset is important. Virgo is the nearest rich cluster, about 50 to 60 million light-years away, and it is a deep reservoir of mass. It contains thousands of galaxies and a massive dark matter halo, with hot intracluster gas glowing in X-rays. In wide images, Virgo is a crowded swarm, a place where galaxies are stripped, distorted, and sometimes quenched. It is a major node in our local web, and it tugs on its surroundings. For decades, Virgo felt like the obvious centre of our supercluster, and the intuition was not wrong. Many nearby galaxies show motions consistent with infall toward Virgo, and the local group itself has a measured peculiar velocity. The cosmic microwave background provides a reference frame, and relative to that frame, our neighbourhood is moving. That motion is often summarised as a dipole anisotropy in the microwave background, a subtle temperature pattern that reveals our drift. It is one of the cleanest signs that we're not at rest in the cosmic frame. But the flow map shows a larger story beyond Virgo, and it complicates the idea of a single centre. The flow lines continue past Virgo toward a broader convergence region, and the vectors do not all terminate at Virgo's core. That region is often called the Great Attractor, a direction in the sky where many galaxies seem to drift. It is not a single object, and it is not a single cluster. It is a gravitational pull from multiple structures, layered along the line of sight like overlapping shadows. The Great Attractor is partly hidden behind the Milky Way's disk, and that is more than a poetic obstacle. Dust and stars obscure optical surveys in the zone of avoidance, creating a band where galaxy catalogues thin out. The sky there looks like a missing piece, as if someone erased data with a broad brush. Yet gravity does not care about obscuration, and peculiar velocities still point that way. Even when we cannot see the structures clearly, we can feel their influence through the drift they induce. As surveys improved, the attractor region became less mysterious, but more complex, and complexity is often the price of clarity. Infrared observations penetrate dust better than visible light, and radio surveys can detect neutral hydrogen in galaxies hidden optically. X-ray observations reveal hot gas in massive clusters, and those clusters mark deep potential wells. Each wavelength adds a layer to the map, and the Great Attractor direction fills in with real objects. It includes clusters and superclusters in the Hydra, Centaurus region. It also connects onward toward the Shapley concentration, an even larger mass over density that deepens the gravitational landscape. Laniakea's definition captures this hierarchy without pretending it is a single-bound system. It says our local flows tend to drain toward a particular basin, and that basin has a recognizable convergence. It also says that basin is embedded in larger-scale structure, where even bigger overdensities can influence the flow. The picture is not a closed circle, it is a cascade where one basin sits near the edge of another, and the edges are defined by where streamlines split. This is where the documentary's central question begins to tighten, and the tone should darken slightly. If even our neighbourhood is defined by invisible gravity rather than visible borders, then the largest claims ahead may be even less object-like. What we call a thing may be a pattern, and what we call an edge may be a mathematical surface. The universe is not obligated to provide crisp outlines for our categories. It provides fields, and we decide how to slice them. We need a scale anchor before we climb, because without it the numbers blur together. Laniakea spans roughly 500 million light-years across in diameter, depending on the exact definition and dataset. That is about 150 megaparsecs in round numbers, a unit astronomers use because light-years become unwieldy. In a visualization, this is a volume so large that individual galaxies become grains of dust and clusters become bright embers. Filaments stretch like faint smoke trails between nodes. 500 million light-years is enormous by any human standard, and the mind resists it. Light would need 500 million years to cross it, and civilizations rise and fall in a blink compared to that time. Continents drift, species evolve, and entire lineages vanish while a photon is still travelling across our local basin. Yet cosmology calls it local, and that word is not arrogance. It is a reminder of how much larger the observable universe is. It is local because the observable universe is far larger, and because we can still measure individual motions here. The cosmic microwave background comes from nearly 14 billion years of look-back time, a relic glow from when the universe became transparent. The co-moving diameter of the observable universe is about 93 billion light-years, a number that includes the expansion of space during the light's journey. Compared to that, Laniakea is a neighbourhood, not a kingdom. It is close enough that peculiar velocities are measurable rather than negligible. So Laniakea becomes a bridge between scales, and that is part of its value. It is a nearby test case where we can measure individual galaxy motions with multiple methods, then compare them. It is also a bridge between small-scale intuition and the truly extreme structures later, where we must rely more heavily on statistics. Here, we can still talk about specific clusters and specific directions. Later, we will talk about patterns that span so far they challenge the meaning of connected. There is another reason Laniakea matters, and it is methodological as much as it is cosmic. It shows how cosmology defines structure operationally, not just aesthetically. A supercluster is not always a bound object that will collapse. It can be a region of correlated motion in an expanding space-time, a place where the velocity field has a shared destination. This definition is less intuitive than a bright patch on a map, but it is closer to the physics. That distinction protects us from a common misunderstanding that even careful viewers can carry. A map of dense galaxy regions can suggest a solid continent, as if the universe has tectonic plates. In reality, much of a supercluster is still expanding overall, even while parts fall inward locally. Expansion does not stop at the edge of a cluster. It is the background behaviour of space itself, and gravity must fight it to bind matter together. Gravity competes with expansion, and the competition depends on scale and density, which is why clusters and superclusters behave differently. Clusters like Virgo are virialized and bound, with galaxies orbiting in a deep potential well and random motions that reflect equilibrium. Their hot gas, visible in X-rays, is trapped by gravity, and it carries a record of the cluster's mass. Superclusters are often not virialized, and their outskirts may never become bound. Some parts may eventually collapse, while other parts will thin out forever as expansion wins. So what does it mean to belong to Laniakea, if belonging does not guarantee a shared fate? It means that, after subtracting the Hubble flow, a galaxy's peculiar motion tends to point toward the same basin. It means the galaxy is on the same gravitational drainage system, even if the water never reaches the sea. The definition is about present-day flow, not about ultimate collapse. It is a snapshot of dynamics, not a promise of destiny. This is a subtle but powerful way to define an object, and it changes how we picture the cosmos. It is closer to meteorology than architecture, because patterns of motion define the system. You define a storm by wind patterns, not by a fence, and you define a basin by where the currents converge. In visuals, the supercluster becomes a choreography of arrows. The universe stops looking like a static map and starts looking like a moving fluid. The flow approach also exposes the hidden mass distribution, which is where the mystery deepens. Luminous galaxies trace some of the matter, but not all of it, and not even most of it. Dark matter dominates the gravitational field, and the velocity field responds to the total mass, visible and invisible. When galaxies drift in coherent streams, they are responding to a potential shaped largely by dark matter. The light is a tracer, but gravity is the author. In that sense, Laniakea is a dark matter map drawn indirectly, and that is one of its quiet triumphs. It is a reconstruction of the nearby gravitational potential, inferred from motion rather than from light. It turns galaxy motions into a contour map of invisible structure, like mapping a valley by watching how rainwater flows. The contours are not drawn with ink, They are drawn with residuals, with differences between expected and observed velocities. The reconstruction is not perfect, and the documentary should admit that without weakening the wonder. Peculiar velocity distances have large uncertainties, and those uncertainties grow with distance. Malmquist bias and selection effects can skew inferred flows if not corrected carefully, because brighter objects are overrepresented in flux-limited surveys. The velocity field also depends on smoothing choices, and smoothing is a double-edged tool. Too much smoothing erases real features, and too little turns noise into fake eddies. Even the choice of how to interpolate between sparse data points can matter, because galaxies are not evenly distributed across the sky. Some regions are well sampled, while others are thin, especially near the zone of avoidance. Laniakea is a best fit description, not a hard-edged truth, and its exact boundary can shift as catalogues improve. Yet the core message survives those details. The local universe is organised by converging flows, and the boundary is a watershed surface where streamlines peel away toward other basins. That boundary also reframes older supercluster names, and it does so without dismissing their historical usefulness. The local supercluster becomes a partial view of a larger basin, a density-based label that captured something real but incomplete. Virgo becomes a major node inside Laniakea, not the final destination of every local flow. The older map was not wrong, but it was drawn with a different rule. The newer map asks a different question. Not where galaxies are, but where they are going. We can now place key landmarks in one coherent narrative, and the narrative has a direction. The Milky Way sits in a small group on a filamentary network surrounded by dwarfs and neighbouring groups. That network feeds toward Virgo and other nearby groups, and the larger drift points toward the Great Attractor region. Each landmark is a step in a gravitational cascade, where small groups fall toward clusters and clusters align along filaments. The map is not drawn by brightness alone, but by the direction matter is moving. In visuals, the viewer should see the cosmic web as a living structure. Filaments glow faintly, clusters burn brighter, and arrows slide along the threads like migrating schools of fish. The watershed boundary should look like a translucent membrane, not a wall, cutting through space where the flow changes allegiance. When the camera rotates, the boundary should remain defined by vectors, not by a visible seam. The sensation should be that we are watching a hidden weather system on the largest scales. This is where the tone should deepen into mystery, because the most important borders in our neighbourhood are invisible. They are defined by equations and residuals, by tiny deviations in redshift that reveal a hidden landscape. The viewer should feel the implication, not as a lecture, but as a quiet unease. If the nearest supercluster is already a concept built from motion, then the larger structures may be even more dependent on how we choose to define connectedness. Are we discovering objects, or are we choosing coordinate systems for patterns? Laniakea also previews a coming tension, and it is worth holding that tension in the mind. The cosmological principle expects homogeneity on the larger scales, meaning that the universe should look statistically similar in every direction when averaged enough, yet the flow map shows coherent motion across hundreds of millions of light-years, driven by mass concentrations we cannot fully see. That tension is not a contradiction, but it is a pressure point. Coherent flows can exist within an overall homogeneous universe, as long as they are statistical fluctuations within expected limits. The question is where those limits break, and whether our definitions make them seem to break sooner. How large can a coherent basin be before it stops being a local feature and becomes a challenge to the model? How far can a filament stretch before connected becomes a matter of algorithm choice rather than physics? These are not questions with dramatic answers in this chapter, but they are questions that sharpen the viewer's attention. They also prepare us for later claims about walls, chains and structures that seem to span impossible distances. We can now connect back to Chapter 1's warning about definitions, because Laniakea is a demonstration rather than an argument. Size can mean diameter, mass, or coherence, and each choice yields a different map. Laniakea's size is a coherent size defined by shared flow toward a basin. That makes it a map legend for the rest of the series, a reminder to ask what rule produced the boundary. When we later hear about walls and enormous associations, we will ask the same questions. Are they defined by density, by connectivity algorithms, or by dynamics? Dynamics is the hardest to fake, because motion integrates gravity over time, and gravity is the underlying sculptor. Yet dynamics is also hard to measure at great distances, because peculiar velocities become tiny compared to Hubble recession. The farther away we look, the more the expansion dominates the redshift, and the more distance errors swamp the residuals. That limitation will matter later, and it will force other definitions to take over. For now, we can still do the hard thing, and that is why this chapter matters. For now, Laniakea gives us a grounded starting point, and it does so without pretending to be a final answer. It is vast enough to humble intuition, yet close enough to measure with multiple methods and cross-checks. It is our first giant that is defined by gravity's choreography, not by a bright outline. It is also a reminder that the universe is not arranged for our convenience. Its structures are processes, and their borders are often mathematical. The chapter ends by turning the map outward. If our home is a basin in a field of gravitational rivers, then the next question is unavoidable. What happens when many basins connect, and the rivers converge into supercluster empires? If those empires stretch too far, they challenge the idea that the universe smooths out, at least on the scales we expect. They force us to ask whether the giants are real objects, statistical illusions, or signs of missing physics. They also force a quieter question, one that sits beneath the spectacle. When we name something in the cosmos, are we naming a thing, or are we naming a pattern in motion? The climb continues, and the next structures will test every definition we have used so far. Laniakea taught us to define structure by motion, not by outlines. Now we travel farther, to a region whose mass is harder to ignore. The Shapley Supercluster sits in the nearby universe, roughly 200 megaparsecs away, far enough to feel remote yet close enough to chart. It lies in the direction of Centaurus, beyond the Great Attractor line of sight, where the sky already feels crowded with structure. In catalogues it appears as a dense complex of rich clusters, not a single tidy object, and that untidiness is the point. On a visualization, Shapley does not look like a lone island. It looks like a knot, threads of galaxies tightening into a bright granular core. The eye is drawn to multiple peaks in density, like mountain ranges seen from orbit, separated by valleys that are thinly populated but not empty. Shapley is called a supercluster complex because it is layered and hierarchical, a nested pattern rather than a single body. It contains multiple massive clusters and groups, embedded in thick filaments that feed them over cosmic time. Its core concentration is often labelled the Shapley concentration, a peak in galaxy density and inferred mass that dominates regional maps. Historically, Shapley's name carries a quiet echo of earlier astronomy. Harlow Shapley mapped the Milky Way's globular clusters to locate our galaxy's centre, and now his name marks a much larger centre of gravity. It is a reminder that every generation redraws the map outward, then discovers the map is still incomplete. On these scales, nearby means we can still map individual clusters with detail, including their member galaxies and hot gas halos. It also means the structure is close enough to matter for local flows, at least in principle. The question becomes uncomfortable. How far can a distant mass concentration reach into our neighbourhood? The cosmic web provides the context that makes Shapley plausible, because the universe does not grow structure at random. Gravity amplifies tiny early density ripples into a network of filaments and voids, guided by dark matter's invisible scaffolding. Matter streams along filaments and piles up where filaments intersect, and those intersections become nodes that mature into clusters and superclusters. Filaments are not rigid cables, and voids are not empty holes, even when they look black on a survey map. They are statistical outcomes of growth in an expanding universe with dark matter, where density contrasts evolve under competing influences. The web emerges because collapse is anisotropic, meaning matter falls fastest along one axis, then another, leaving sheets and strands. In simulations, you can watch this happen as if time-lapse photography were possible. A diffuse cloud first flattens into a wall, then fractures into filaments, then drains into compact nodes. The process is not engineered, yet it produces architecture, an emergent geometry written by gravity and expansion. This is why walls and chains appear in surveys without being designed. If you sample a lumpy field, overdensities connect along preferred directions, because the underlying tidal field sets the lanes of collapse. Algorithms then trace those connections, and the map begins to look like a built environment. The caution from Chapter 1 returns. Connectedness depends on definitions and thresholds. Shapley stands out even under conservative definitions because the mass is concentrated, not merely spread thin across a large volume. Rich clusters there show high galaxy counts and deep potential wells, and several are famous in their own right. The region is a major node in the local cosmic web, comparable to an empire of clusters whose provinces overlap. But calling it an empire raises the central question again. Are we naming a coherent object, or a region where many structures overlap and happen to align in our catalogues? Superclusters are often not fully bound, and their outskirts may never collapse into one final body. Shapley's importance is not a sharp border, it is influence. Influence is measured through gravity, and gravity is measured through proxies, because most of the mass refuses to shine. Light traces stars, but most mass is dark matter and hot gas, and both can dominate the gravitational budget. On supercluster scales, we infer mass by combining several imperfect methods, then asking whether they converge. Agreement between methods is the closest thing to a verdict. Start with the simplest clue, the one that predates modern cosmology. Galaxies and clusters move fast, and their velocity dispersion reflects the depth of the gravitational potential. When you look at a cluster's spectrum, the lines are shifted by expansion, but they are also jittered by orbital motion. We measure redshifts for many member galaxies, then subtract the mean cluster redshift to isolate internal motions. The spread in velocities gives a dynamical mass estimate, often through the virial theorem and related scaling relations. The logic is old and direct. Faster random motions require more mass to keep the system bound. In practice, the measurement is both elegant and fragile. You need enough galaxies to sample the distribution, and you need membership assignments that are not fooled by projection. A few interlopers along the line of sight can contaminate the sample and widen the spread, making the cluster appear heavier than it is. This method also carries assumptions that must be stated aloud. It works best when a cluster is virialized and close to equilibrium, meaning kinetic and potential energies have settled into a steady balance. Mergers can inflate dispersions and bias masses high, especially when two subclusters overlap in redshift space. Shapley's clusters are not all relaxed, and that is part of the story rather than a nuisance. A supercluster is a construction zone, not a finished building, with cranes and dust hidden inside the data. Subclusters fall in along filaments, and the velocity field can be messy, with coherent streams layered on random motion. The mess is evidence of growth, but it complicates clean mass inference. To reduce that ambiguity, we use the hot gas as a second mass tracer, because the gas responds to gravity in a different way. Massive clusters trap intracluster gas at tens of millions of degrees, where atoms are stripped and collisions are violent. At those temperatures, the gas emits X-rays through thermal Bremsstrahlung and line emission, turning gravity into hard light. Visually, an X-ray map of a rich cluster looks like a ghostly atmosphere. The brightest regions trace the densest gas, often centered near the deepest part of the potential well, while faint extensions hint at infill and disturbance. Sometimes you see sharp edges, cold fronts and shock fronts, like weather systems frozen in plasma. X-ray brightness depends on gas density and temperature, and that dependence is steep enough to make dense cores blaze. With spectra, we estimate temperature profiles and total gas mass, and we can track how the gas cools with radius. If the gas is in hydrostatic equilibrium, pressure gradients balance gravity, and the mass profile can be derived from the observed pressure support. Hydrostatic equilibrium is a useful approximation, not a guarantee, especially in regions still assembling. Turbulence, bulk flows, magnetic fields, and cosmic rays add non-thermal pressure that X-rays do not fully reveal. Mergers drive shocks that heat gas and displace it from the dark matter, leaving offsets between the luminous plasma and the true mass peak. These effects usually make hydrostatic masses biased low, even when the X-rays look smooth. Still, X-rays matter because they reveal the depth of the well in a different language. A cluster that is X-ray bright and hot is almost always massive, because only a deep potential can confine such energetic gas. In Shapley, multiple rich clusters show strong X-ray emission, reinforcing the claim of extreme mass concentration. The supercluster does not just contain galaxies, it contains furnaces of plasma. A third method bypasses the light and the gas, and it feels almost unfair in its directness. Gravitational lensing measures mass through its effect on space-time, bending the paths of photons that never interacted with the cluster. Background galaxies appear subtly sheared by foreground mass, and the shear pattern maps the projected mass distribution. Weak lensing is statistical and demanding because the distortions are small and the sky is noisy. Intrinsic galaxy shapes add scatter, and the atmosphere and optics imprint their own distortions that must be modelled and removed. We average over many background sources, calibrate point spread functions, and control systematics in the imaging. When it works, lensing does not care whether matter shines. It counts all mass. Strong lensing is rarer but dramatic, producing arcs and multiple images that look like torn ribbons of light. It probes the densest cluster cores and anchors mass models at small radii, where the potential is steepest. In Shapley's richest clusters, lensing can confirm deep central potentials, and it can expose substructure that dynamics can smear out. Each method has different failure modes, which is why we combine them rather than crown a single winner. Velocity dispersions can be inflated by mergers and contaminated by interlopers. X-ray masses can be biased by non-thermal pressure, especially during active assembly. Lensing can be affected by projection of unrelated structures along the line of sight, stacking mass that is not physically connected. When all three point to high mass, the conclusion hardens. Shapley is not just a visual overdensity, and it is not merely a product of how we draw contours. It is a gravitational landmark, heavy enough to register across independent diagnostics. Now we add a fourth constraint that sounds mundane but is powerful, because it ties local physics to global cosmology. Baryon fractions connect clusters to the cosmic inventory, since baryons are normal matter, and their fraction relative to total mass is expected to approach the cosmic average in massive clusters. In plain terms, big clusters are supposed to be fair samples of what the universe is made of. We measure baryons in two main reservoirs, and both are visible in different ways. Stars in galaxies contribute a smaller fraction, measured through starlight and stellar population modelling. Hot intracluster gas contributes the majority of baryonic mass, measured through X-ray emission, and, in some cases, the Sunyaev-Zeldovich effect, as it imprints a spectral distortion on the cosmic microwave background. From X-ray gas mass and stellar mass estimates, we compute the baryon fraction, then compare it to the cosmic baryon fraction inferred from the cosmic microwave background. If a cluster's baryon fraction is too low, it suggests missing gas, feedback effects, or biased total mass. If it is too high, it suggests underestimated total mass or calibration errors in the gas measurement. This is not just bookkeeping, and it is not a minor correction at the margins. It is a consistency check across scales, where a cluster's internal accounting must agree with the universe's global parameters. Clusters become laboratories where local measurements meet the early universe imprint preserved in the CMB. In Shapley, baryon fractions help test whether the extreme masses are plausible, rather than artifacts of a single method. If multiple clusters show reasonable baryon fractions at high inferred mass, the case strengthens and becomes harder to dismiss. If they do not, we revisit assumptions about equilibrium, projection, and selection, because the universe rarely lets contradictions stand unchallenged. Selection matters because Shapley is famous, and fame can bias samples before we notice it happening. We notice the brightest, richest clusters first, because they announce themselves in optical counts and X-ray flux. We then build narratives around the most extreme regions, and the extremes can feel more typical than they are. The documentary must keep the tension honest, because the universe is lumpy, and our attention is not evenly distributed. Even with that caution, Shapley remains a standout in the nearby universe, and it stands out in multiple wavelengths. Its cluster population is unusually rich, and its mass concentration is unusually high by local standards. It is a node where several filaments converge, and convergence is where gravity writes its boldest signatures. The web does not merely pass through Shapley, it appears to thicken there. Those signatures include motions beyond the supercluster itself. In Chapter 2, we followed peculiar velocities to define a basin, using motion as a boundary where outlines fail. Now we ask whether Shapley contributes to the flows we observe locally, even though it sits far beyond our immediate neighbourhood. The local universe has a measured motion relative to the cosmic microwave background, and that motion is encoded in the CMB dipole. It is a clean reference frame for our drift, because the dipole is a sky-wide signal rather than a local measurement. The question is not whether we move, the question is what mass distribution explains the direction and magnitude. Historically, the Great Attractor was proposed as a major cause of local streaming, a hidden concentration inferred from peculiar velocities. As surveys improved, the picture became layered, and the mystery shifted rather than vanished. The pull is not from one concealed monster, it is the vector sum of many overdensities, spread across distance and direction. Shapley enters as a suspect because it is massive and not too far away in cosmological terms. If it contains enough mass, it can contribute significantly to the bulk flow, adding a distant but persistent tug. If it is less massive, or more extended and less concentrated, its influence weakens and nearer structures dominate. This is where the narrative tension lives, because gravity is long-range but its measurable effects decay with distance. Peculiar velocities become harder to measure as distance increases, because Hubble expansion dominates redshift and the signal becomes a small residual. We're trying to explain a local drift using distant structure, with noisy data in between. The uncertainty is not a flaw in the story, it is the story. We can frame the problem as competing models that are testable, even if none is perfect. One model assigns most of the pull to nearer structures in Hydra, Centaurus, including the region associated with the Great Attractor. Another assigns a substantial fraction to Shapley's deeper potential, treating it as a heavyweight behind the nearer foreground. The difference is not philosophical, it changes how we reconstruct the mass field around us. To test these models, astronomers compare observed velocity fields to predictions from galaxy density fields, using the fact that velocities respond to gravitational potential gradients. They use linear theory on large scales, where the relationship is simplest and the growth of structure is well described. They also use constrained simulations that reproduce local structure, then evolve it forward under a chosen cosmology. The goal is not a perfect replay, but a statistically consistent universe that resembles ours. The comparison is imperfect because galaxies are biased traces of mass, and bias is not a single number. Galaxy density does not equal mass density in a simple way, because different galaxy types populate environments differently and evolve under feedback. Surveys miss faint galaxies at distance, and dust and selection functions reshape what we count. We correct, but corrections carry assumptions that must be stress-tested. X-ray clusters help because they trace deep wells with less ambiguity than galaxy counts alone. Lensing helps because it bypasses bias in light and measures projected mass directly. When Shapley's clusters are included, predicted flows can shift closer to observed ones, especially in the direction of the dipole. That is suggestive, not final, and the gap between suggestive and final is where science lives. There is also a limit built into the cosmological model, and it makes the question sharper. Large-scale bulk flows are expected, but their amplitude has a distribution set by the initial conditions and the growth rate of structure. If observed flows are too large on too big a scale, they can pressure test the model's assumptions. Shapley becomes part of that test because it is one of the largest nearby overdensities we can measure with multiple tools. The deeper point is about how gravity sculpts the web over time. Superclusters are not static monuments, and they are not guaranteed to become single collapsed objects. They are regions where matter is still moving inward along preferred directions, and where the velocity field retains memory of the surrounding landscape. The web is a record of growth, and Shapley is a page where the ink is dark. Yet even here, we must separate two ideas that sound similar, because language can blur physics. A region can be a strong overdensity and still not be bound as a whole, especially when dark energy and expansion set a long-term limit. Clusters within it can be bound and virialized, with galaxies orbiting in a deep well. The supercluster complex can remain a transient pattern in the expanding universe, impressive but not destined to fuse. That distinction matters for the central question about objects, because our brains want clean nouns. The universe can build enormous patterns without building a single coherent body, and it can create a gravitational landscape where flows converge without guaranteeing a final collapse. When we name a supercluster, we're often naming a region of influence rather than a future galaxy. So what is Shapley, operationally, when we strip away the romance and keep the measurements? It is a nearby high-mass node in the cosmic web, with a core of rich clusters and a surrounding network of filaments. It is a plausible contributor to large-scale streaming motions, depending on how its mass is distributed in depth. It is also a case study in how we infer mass when most of the mass is invisible. We now tighten the measurement theme into a single takeaway, because the methods form a linked chain. On these scales, mass is inferred from 3 connected observables, each translating gravity into a different signal. Light counts galaxies and traces stellar content. though it is biased and incomplete. Motion reveals the depth of potential wells through velocity dispersions and coherent flows, even when the matter itself is dark. Hot gas reveals the thermal imprint of gravity through X-ray emission and pressure support. Lensing ties them together by mapping the total mass directly, turning background galaxies into test particles of curved space-time. When the maps agree, the structure is not just a cartographic artifact, and it is not merely a product of our chosen thresholds. It is a real overdensity in the matter field, heavy enough to be seen from several angles. Shapley also previews a shift in storytelling scale, and the shift changes how we build confidence. Laniakea was defined by local flows we can still measure galaxy by galaxy, with distances that feel almost personal. Shapley pushes us toward a regime where dynamics becomes more statistical, because the volume is larger and the signals are fainter. We rely more on surveys, cross-correlations, and ensemble methods. That shift is not a loss of certainty. It is a change in how certainty is built. We trade individual distances for large samples, and we trade crisp membership for probability. We trade a single boundary for a set of consistent signals that overlap in the same region of space. The story becomes less about drawing a line and more about weighing evidence. Before we leave Shapley, we return to the documentary's hook because the hook is not only about size. What if the universe contains structures so vast they shouldn't exist, at least not in the numbers we expect? Shapley does not break the rules by size alone, but it threatens our comfort by showing how much mass can gather nearby. It also forces a question about reach. How far influence can extend before it dissolves into noise? If Shapley can tug on our region, then the web is not just scenery. It is an active gravitational field, shaping motions across hundreds of millions of light years, even while space itself expands. The cosmos becomes a place where distant concentrations can still matter, and where near and far are measured in acceleration as much as in distance. This is the step up in scale and power that Chapter 3 must deliver. We move from our basin to a heavier node, from local choreography to a broader gravitational argument. We also move from naming structures to interrogating how we know they are massive, and how we know the influence is real. The next step is to go smaller in size but hotter in physics. If superclusters are the great nodes of the web, then galaxy clusters are the furnaces. They are where matter falls in, heats up, and sometimes refuses to cool. We follow that heat inward, because temperature is a mass signal, and mass is the engine of structure. The story turns from the empire to the foundry, where gravity's work becomes visible in gas, shocks, and the hard light of X-rays. Chapter 3 ended at the foundry door. Now we step inside a cluster that burns too bright. The Phoenix cluster sits billions of light-years away, a massive node in the cosmic web. On a wide-field map, it looks like a bright knot where faint filaments converge, an intersection where matter has been arriving for eons. It is famous because it is exceptionally luminous in X-rays, even by cluster standards. In X-ray images, the core does not merely glow, it dominates, as if the cluster has a hot heart turned outward. It's also famous because its core behaves like a cooling flow system turned up past expectation. Compared with typical rich clusters, Phoenix shows unusually high inferred cooling rates and unusually intense star formation. That pairing is what makes astronomers pause, because the two signals should not coexist so loudly for long. Either the cooling should have been stopped, or the consequences should already have reshaped the core beyond recognition. This is where the central question tightens again. How can the universe build giants that look stable, yet run extreme internal engines? What do these engines reveal about the limits of our models for structure growth and energy balance? When we call something a cluster, we imply a kind of permanence, a long-lived object with a predictable interior. Phoenix asks whether that confidence is earned, or whether stability is sometimes only a surface impression. A galaxy cluster is not just a crowd of galaxies. Most of its normal matter is not in stars, but in a vast atmosphere between galaxies. This is the intracluster medium, or ICM, a plasma filling the cluster potential well. It is thin by laboratory standards, yet it outweighs the stars in the member galaxies. If you could see it with your eyes, it would not look like smoke or fog. It would look like emptiness that somehow has weight. The ICM is heated to tens of millions of Kelvin by gravity. As matter falls in, potential energy becomes thermal energy through shocks and compression, nature's way of turning motion into heat. At these temperatures, atoms are highly ionized and collisions are energetic. Electrons and ions ricochet through the plasma, and the gas behaves less like air and more like an electrically conducting fluid. The gas emits X-rays through thermal Bremsstrahlung and line emission from heavy ions. Bremsstrahlung is braking radiation, produced when fast electrons are deflected by ion electric fields. Line emission adds sharp spectral fingerprints from elements like iron, silicon, and sulfur, whose remaining electrons jump between energy levels. Those lines are not decorative. They let astronomers measure temperatures, densities, and chemical enrichment with surprising precision. That is why clusters glow even when their galaxies look faint. Galaxies are bright in optical light, but they occupy little volume and contain a minority of baryons. The ICM fills the space and radiates steadily in X-rays, tracing the deepest gravitational wells. When we map a cluster in X-rays, we are mapping the thermal imprint of gravity. We are also, indirectly, mapping where dark matter has sculpted a basin deep enough to hold a cosmic atmosphere. Phoenix stands out because that imprint is extreme. Its X-ray luminosity signals a dense hot core and a deep potential. In the central regions, the X-ray surface brightness rises steeply, like a spotlight aimed at the cluster's center. That brightness is not just temperature, it is density, because X-ray emission scales roughly with the square of the gas density. A modest increase in density can therefore look like an enormous increase in radiated power. Its central regions radiate energy so efficiently that, on paper, the gas should cool quickly. Cooling should reduce pressure support, allowing more gas to flow inward. Inward flow should raise density, which increases X-ray emission, which accelerates cooling again. In the simplest picture, the core becomes a self-reinforcing drain, pulling the ICM inward as it loses heat. This feedback loop is the classic cooling flow picture. If nothing stops it, a cluster core should condense enormous amounts of cold gas. That cold gas should form stars at rates far higher than we usually observe. The simplest models predict cooling rates that would build a giant galaxy too quickly. They also predict strong signatures of gas cooling through intermediate temperatures, visible as specific X-ray and ultraviolet lines. For decades, this mismatch became the cooling flow problem. X-ray data implied short cooling times in many cluster cores, sometimes far shorter than the age of the cluster itself. Yet the expected reservoirs of cold gas and the expected star formation were missing or modest. Something was heating the gas, preventing runaway cooling. The problem became a turning point, because it forced astrophysicists to treat clusters as active systems rather than passive containers. Historically, this was not a small correction to a model. It was a reorientation. Early cooling flow estimates in the late 20th century suggested hundreds of solar masses per year could cool in some cores. As X-ray spectroscopy improved, the missing cooling lines became harder to ignore. The universe was telling us that energy was being injected back into the gas, and it was doing so in a structured, repeatable way. The leading answer is AGN feedback from the central galaxy's supermassive black hole. In many clusters, the brightest cluster galaxy sits at the potential minimum, like a heavy stone at the bottom of a bowl. Gas that cools and sinks can feed the black hole, triggering jets and outflows. Those jets inflate cavities in the ICM and drive shocks and sound waves. In X-ray images, the cavities appear as dark bubbles, holes punched into the glow. The energy budget can be enormous, even when the jets are narrow. Mechanical power couples to the surrounding plasma and offsets radiative losses, not by shining, but by pushing. The cluster core becomes a thermostat with a violent control system. Cooling feeds the AGN heats the gas, and heating reduces cooling. The thermostat metaphor is imperfect, yet it captures the logic, a self-adjusting loop that can keep gas hot without blowing it away. This is the standard story, and it usually works. Many cool core clusters show X-ray cavities aligned with radio lobes, where relativistic electrons spiral in magnetic fields and glow at long wavelengths. The implied jet power often matches the cooling luminosity within uncertainties. The result is not perfect balance, but a regulated state where some cooling and star formation continue at reduced levels. The core flickers between episodes of condensation and episodes of reheating, never settling into silence. Phoenix appears to strain that regulation. Observations indicate a core with very high X-ray brightness and short cooling time, They also indicate unusually high star formation in the central galaxy, compared with most clusters at similar mass. In optical and infrared views, the central galaxy can look bruised with blue light and dust lanes, signs of young stars forming behind veils of soot. The system looks like a case where cooling is winning more often, or where feedback is delayed, intermittent, or inefficient. We need to be careful with what cooling rate means. X-ray spectra can imply how much gas is losing energy, but turning that into a mass deposition rate depends on models of multiphase gas. Star formation rates depend on dust corrections and assumptions about stellar populations, which can shift numbers by factors. Even so, Phoenix remains an outlier in multiple analyses, and the outlier status is the point. It refuses to blend into the population where the thermostat seems to hold. Phoenix forces a sharper question. If AGN feedback is the universal solution, why does this core look so active? Is it a rare phase caught at the wrong time, or a sign that feedback can fail under certain conditions? Is the cluster's environment feeding the core faster than the black hole can respond? And if the response is late, what does late mean when the relevant timescales range from millions to billions of years? To answer, we zoom out to the cluster's true structure. A cluster is a bound object, because gravity has beaten expansion inside a virial radius. Galaxies orbit with high-velocity dispersions, and the ICM is trapped in the same well. The cluster's mass is dominated by dark matter, which provides the scaffolding for everything else. In a visualization, galaxies are sparks, but dark matter is the invisible forge that holds the shape. Dark matter is not a detail in this story. It shapes the potential that heats the gas, sets the escape speed, and controls how mergers stir the core. The ICM temperature is a proxy for the depth of the dark matter halo. The X-ray brightness depends on gas density, which depends on how baryons settle into that halo. Even the central cooling time depends on how steeply the dark matter cusp compresses the gas toward the center. In the cosmic web, clusters form at filament intersections. Matter streams along filaments and piles into nodes, building halos over time. Mergers are common, and they drive shocks that heat the ICM further. In simulations, these shocks look like ripples and arcs, sweeping through the gas like weather fronts. Even a relaxed-looking cluster carries the memory of past collisions in its temperature structure and entropy profile. Phoenix is a case study in how the largest bound structures behave. It shows dark matter's role as a stable container and gas physics as a restless occupant. It shows that the cluster scale is big enough for equilibrium in gravity, yet small enough for violent disequilibrium in the core. A cluster can be dynamically old, while its center remains thermodynamically young, still negotiating how to share energy. This is also where we distinguish clusters from superclusters. A cluster is gravitationally bound and virialized in its inner regions, meaning orbital motions and gas pressures have largely settled. A supercluster is often a pattern of overdensity and flow, not a single bound object. Superclusters can contain many clusters that are individually bound, while the larger complex continues to expand overall. On the largest maps, the universe draws shapes that resemble organisms, yet many of those shapes are only temporary alignments. That contrast matters for the documentary's theme about objects. The universe can build structures that look like entities on a map, yet lack a shared fate. Clusters are closer to true objects, because they are bound and long-lived. Phoenix is a reminder that even true objects can behave like engines, not monuments. The outside can look calm, while the inside negotiates a relentless energy bill. Inside a cluster, the ICM is the main stage for energy exchange. Radiative cooling removes thermal energy and lowers entropy. Gravitational compression and shocks add energy and raise entropy. AGN feedback injects mechanical energy and redistributes entropy through bubbles, turbulence, and mixing. Each process leaves a different texture in the gas: edges, ripples, cavities, and gradients that X-ray telescopes can read like a weather report. Entropy is the quiet variable that controls the drama. Low entropy gas sinks toward the center and can cool rapidly because it is dense and radiates efficiently. High entropy gas resists condensation and stays buoyant, like a warm parcel in Earth's atmosphere. Feedback that raises core entropy can suppress cooling without needing to expel all the gas. In that sense, the battle is not simply about heat, but about where the heat sits in the stratified atmosphere. Phoenix suggests a core with a large supply of low entropy gas. That can happen if the cluster has a dense, cool core that survived mergers without being shredded. It can also happen if gas is being funneled inward efficiently, replenishing the cooling region. In either case, the core becomes a furnace where inflow, cooling, and feedback compete. The furnace is not a metaphor for fire, but for throughput, energy in, energy out, and matter cycling through phases. The battle is not only thermal. Magnetic fields can drape around bubbles and suppress conduction across boundaries, keeping hot and cool regions from quickly equalizing. Turbulence can mix hot and cool phases, changing how quickly gas condenses into clouds. Cosmic rays can add pressure support and alter how shocks dissipate energy. These ingredients complicate the thermostat, because they change how efficiently energy spreads through the core. Even with these complications, the basic accounting remains. X-ray emission is energy leaving the gas, carried away by photons that will never return. Something must replace that energy, or the gas must cool and condense. Phoenix looks like a system where both are happening at high rates, which is why it feels like a violation of common sense. It is not that physics breaks, it is that multiple channels are running near their upper limits at once. We can frame Phoenix as a snapshot of a cycle. Cooling builds cold gas and feeds star formation in the central galaxy, producing young stars that shine blue and heat surrounding dust to infrared glow. Cooling also feeds the black hole, but the response may lag behind the inflow. When the AGN turns on strongly, it can overheat the core and shut down cooling for a time. Then, as the core relaxes, cooling resumes and the cycle begins again. If we catch the cluster between these phases, we see extremes. We see a bright X-ray core that implies rapid cooling. We see star formation that implies cold gas is actually forming, not merely predicted. We may also see signs of feedback that has not yet fully caught up, or is depositing energy in the wrong places. Jets can overshoot, heating gas at larger radii while the innermost region continues to condense. This interpretation keeps the standard model intact, but it raises the stakes. If Phoenix is a rare phase, then surveys should find few like it, and the rarity itself becomes a measurement of duty cycle. If it is more common at earlier cosmic times, then feedback may evolve with redshift and environment. Either way, Phoenix becomes a stress test, not a curiosity. It asks whether our feedback recipes are truly predictive or merely descriptive after the fact. The stress test extends to how we measure cluster mass and structure. X-ray temperature and luminosity scale with mass, but they are sensitive to core physics and to how relaxed the gas really is. Cooling cores can boost luminosity without proportionally increasing total mass. That can bias mass estimates if we rely on simple scaling relations, especially in surveys where detailed core modelling is impossible. A cluster can look heavier in X-rays simply because its centre is more efficient at radiating. Lensing helps by measuring mass more directly, independent of gas state. Gravitational lensing distorts background galaxies into subtle arcs and shears, turning the cluster into a natural optical element. Velocity dispersions of galaxies provide another check, though they can be disturbed by mergers and substructure. The point is not to litigate one cluster's exact numbers. The point is that extreme baryonic physics can masquerade as extreme size if we are careless. Phoenix also connects back to the opening hook about objects that shouldn't exist. The cluster itself does not violate the cosmological principle by its size alone. Its terror is internal, a core that radiates and cools so fast it threatens equilibrium. It is a giant that seems to burn its fuel in public, broadcasting its losses as X-ray light across billions of light years. The spectacle is not just brightness, but urgency, energy leaving faster than we expect a stable system to allow. We should also say what is not happening. The ICM is not a normal flame, and it is not burning chemically. The heat is gravitational and mechanical, and the light is X-rays from plasma. The furnace metaphor is about energy flow, not combustion. Yet metaphors matter because they guide intuition, and Phoenix demands an intuition that includes invisible heat and invisible pressure. Still, the metaphor earns its place because the core is a conversion engine. Gravity converts infall into heat. Radiation converts heat into X-ray photons that escape forever. Feedback converts accretion into jets that punch the gas and reshape the core. In a layered visualization, you can almost see the bookkeeping: arrows inward for inflow, arrows outward for jets, and a steady leak of light in every direction. At cluster scale, these conversions happen inside a bound container. That container is one of the largest gravitationally bound objects in the universe, assembled from countless smaller pieces. It is large enough to hold thousands of galaxies and a vast plasma atmosphere. It is also small enough that a single central black hole can influence the thermodynamics of the whole core. That disproportion, one object steering the fate of so much gas, is one of the strangest hierarchies in nature. That last fact is the bridge to the next chapter. If clusters are powered and regulated by central engines, then the engines deserve their own descent. We have been talking about feedback as a mechanism, but we have not met the source. Phoenix points us inward to the brightest cluster galaxy and the AGN at its centre. It suggests that the black hole is not a passive sink, but an active governor of a cluster's baryons. It also suggests that the governor can slip, allowing brief periods of runaway cooling and starburst. When that happens, the cluster does not stop being a bound object, but its core becomes a laboratory for extremes. How close can a cooling flow come to running away before the jets answer? How much star formation can ignite before the energy balance tilts back? And when we see Phoenix, are we watching a rare accident or a common phase that we have simply been too slow to catch? So we end with a narrowing tunnel of scale. From supercluster empires, we move to bound cluster furnaces. From the furnace, we move to the engine room, where gravity becomes a point source. The next step is unavoidable. To understand how the largest bound structures stay hot, we must confront black holes so massive they redefine the word monster. Phoenix pushed us toward the engine room where a cluster's fate can hinge on one object. Now the scale narrows again, from megaparsecs to a single point of darkness, an address in space-time rather than a place. TON 618 is not famous because it looks large in the sky. It is famous because it concentrates an absurd amount of mass into one gravitational well, and it does so at a time when the universe was still young. We meet it as a quasar, a hyperluminous beacon from the distant universe. The light is not from the black hole itself, but from matter falling toward it, converting gravity into glare. A quasar is an active galactic nucleus running near its limits, and the word itself carries history. In the 1960s, astronomers realized some stars had enormous redshifts, and the universe suddenly gained a new class of engines. Gas spirals inward, heats up, and radiates across the spectrum before crossing the horizon. Friction is not quite the right word, angular momentum transport is, but the plain truth is simple: the plunge releases energy. In the accretion disk, orbital speeds are a significant fraction of light speed, and the inner regions are ruled by relativity. Magnetic turbulence, often described by the magneto-rotational instability, helps the disk shed angular momentum so gas can fall. TON 618's luminosity is extreme, and its spectrum is unmistakably quasar-like. That brightness is the clue that a supermassive black hole is feeding aggressively, because only deep gravity wells can pay that energy bill. Visually, the quasar is a needle of light in a field of faint galaxies. In a simulated fly-in, the host becomes a dim haze while the nucleus burns white-blue, and the surrounding intergalactic medium glows in thin, ghostly filaments. Its nickname, the monster black hole, is not a marketing flourish. It reflects mass estimates that reach tens of billions of suns, numbers so large they strain intuition even before we ask how they formed. This chapter pivots the documentary's terror of size from width to density. The question becomes how much mass can be packed into one region of space-time before our familiar categories stop helping. We cannot photograph the black hole directly at this distance, and we do not need to. We weigh it by reading the motion and physics of the gas it controls, the way a storm is measured by the wind. Start with the quasar's broad emission lines, produced in fast-moving gas near the centre. The line widths encode velocities through Doppler broadening, where light from approaching gas shifts blue and receding gas shifts red. On a spectrum plot, the lines look smeared and swollen, as if the atom itself were vibrating. In truth, it is the gas that is moving, thousands of kilometers per second, inside a region too small to resolve. If the gas is gravitationally bound to the central mass, higher velocities imply a deeper potential well. That logic is the same gravity we used for clusters, compressed inward until the scale becomes almost cruel. The challenge is that we need a size scale for the emitting region, not only a velocity. Mass follows from a virial estimate, roughly m proportional to v squared times r, and the missing piece is r. Reverberation mapping provides the key idea, even when direct campaigns are difficult. Variability in the central continuum echoes in the lines after a light travel delay, like thunder arriving after lightning. That delay gives an effective radius for the broad line region, because light can only cross so much distance in so much time. Combine that radius with the line width, and the black hole mass estimate emerges from timing and speed. For many quasars, we rely on scaling relations calibrated by reverberation mapping. We use single epoch spectra, line widths, and luminosity as a proxy for radius, because brighter nuclei tend to have larger broadline regions. Those relations are empirical, built from nearby active galaxies where monitoring is feasible. They are then extended outward in redshift, which is powerful, yet it also imports assumptions about how quasar structure evolves. The method is powerful and imperfect, and the caveats must be stated. Geometry, inclination, radiation pressure, and non-virial motions can bias the inferred mass, and each bias can lean the estimate in a different direction. If the broadline region is more disk-like than spherical, then viewing angle matters. A system seen more face-on can look artificially narrow, while an edge-on view can inflate velocities, an observational twist that hides inside the line shape. Different lines trace different zones, and the broadline region is not a rigid shell. It is a structured environment shaped by winds, turbulence, and changing ionization, with clouds and streams responding to a changing radiation field. In some quasars, ultraviolet lines show strong asymmetries that hint at outflows. In others, the profiles are more symmetric, suggesting more gravitationally dominated motion, and the balance between these behaviors becomes part of the uncertainty budget. Accretion disk physics adds another constraint, because luminosity is tied to how fast mass falls in. The disk converts gravitational energy into radiation, with an efficiency set by relativity, and that efficiency depends on spin and the inner disk radius. If we know the luminosity and assume an efficiency, we infer an accretion rate. That rate does not directly give mass, but it checks whether the engine is plausible, because the fuel must be available and the flow must be stable. For TON 618, the numbers point the same direction across methods and calibrations. The central mass is enormous, and the quasar is bright because the well is deep enough to turn infall into a lighthouse. There is a particular visual grammar to this inference. We show spectra, then a schematic of gas orbits, then a simple equation, and the viewer feels the invisible becoming measurable, an object defined by what it makes other matter do. We should be clear about what enormous means in a black hole context. A black hole's size scales linearly with mass through the Schwarzschild radius, which is the radius of a non-rotating event horizon. One solar mass corresponds to about 3 kilometers of Schwarzschild radius. Multiply by billions, and the event horizon becomes a structure on solar system scales, even though it remains tiny compared with any galaxy. For a black hole near 66 billion solar masses, the Schwarzschild radius is on the order of 200 billion kilometers. That is roughly 1,000 astronomical units, a number that stops being abstract when we place it on a familiar map. That radius is not the orbit of gas in the disk, and it is not the extent of the quasar. It is the boundary beyond which light cannot return, the last surface from which information can still reach the universe. 1,000 AU is a visceral anchor because it competes with the outer solar system. It is tens of times farther than Neptune, and comparable to the inner Oort cloud where comets drift in deep freeze. Imagine replacing the Sun with TON 618's horizon, and then drawing the known planets. The inner system would vanish into insignificance, and even the Kuiper belt would seem like a thin ring sketched close to the center. Yet the horizon is still a point compared with galaxies and clusters. The terror comes from the density, because the mass is concentrated into a region that's small, and compactness is what makes gravity ruthless. Density is not just a metaphor here, because gravity cares about compactness. The deeper the well, the more violently it can accelerate matter and bend light, and the more extreme the tidal forces become near the center. Even the accretion disk's light carries signatures of that environment. In principle, relativistic effects can skew line profiles and shift energies because time runs differently and photons climb out of a steep gravitational redshift. This is where the documentary's central question tightens again. How can the universe build objects that seem to defy our models when the object is almost pure mass and the clock is running fast? TON 618 sits at high redshift, meaning we see it far back in time. The light left when the universe was young, and the growth clock was still running, with galaxies assembling and gas still abundant. High redshift also means the light has been stretched by expansion. The quasar's ultraviolet emission arrives shifted into optical wavelengths, and the spectrum becomes a coded message written by cosmic time itself. That creates the growth problem, which is not about measurement technique. It is about whether standard accretion can assemble such a mass quickly enough, given the limited age of the universe at that epoch. The Eddington limit sets a natural pace for luminous growth. As a black hole brightens, radiation pushes outward on in falling ionized gas, because photons transfer momentum when they scatter off electrons. At the Eddington luminosity, radiation pressure balances gravity for spherical inflow. Accretion can continue, but it self-regulates around a characteristic rate, and that rate becomes a kind of speed limit for bright growth. If a black hole accretes steadily at the Eddington rate with typical radiative efficiency, its mass grows exponentially. The e-folding time is tens of millions of years, which sounds generous until you multiply it by the needed steps. Exponential growth sounds fast until you count the required doublings. Reaching tens of billions of solar masses demands many e-foldings without long interruptions, and the early universe is not known for calm continuity. That requirement collides with a messy early universe. Fuel supply, feedback, and galaxy mergers all complicate the idea of smooth, uninterrupted accretion, and each complication can steal time from the growth ledger. Seed black holes are the starting point, and seeds may come in different sizes. One path begins with stellar remnants of the first massive stars, born from primordial gas with almost no heavy elements. Those population 3 remnants might start at tens to hundreds of solar masses. They must then grow through accretion and mergers inside early galaxies, where dense gas can feed them but also form stars that compete for the same material. Another path proposes direct collapse black holes, formed when pristine gas collapses without fragmenting into stars. Those seeds could start at 10,000 to 1 million solar masses, a head start that changes the arithmetic immediately. Direct collapse reduces the number of required e-foldings, but it demands special conditions. The gas must avoid cooling pathways that trigger star formation, which often means suppressing molecular hydrogen, so the cloud stays warm and monolithic. Mergers add another channel, because galaxies merge frequently at early times. Their central black holes can eventually coalesce, stepping mass upward in jumps, and the surrounding chaos can funnel fresh gas toward the center. But mergers are not free mass, because binaries can stall and gravitational waves carry energy away. The timing depends on dense stellar and gas environments, and on whether the pair can shed angular momentum efficiently. Super Eddington accretion is often invoked as a loophole. If inflow is thick and photon-trapped, the black hole can gain mass faster than luminosity suggests, because radiation can be carried inward with the gas instead of escaping. That regime may occur in brief episodes, especially in gas-rich early galaxies. The puzzle is whether it can persist long enough, often enough, to build a monster without the system blowing itself apart. Feedback is the opposing force that makes the puzzle sharp. The same radiation and winds that announce a quasar can heat and expel the fuel, turning the surrounding gas from a meal into a storm. A quasar can therefore choke itself, limiting its own growth. TON 618 implies either exceptional fueling, exceptional timing, or exceptional initial conditions, some combination that kept the engine fed while the universe was still assembling. It is worth lingering on what fueling means in practice. Gas must lose angular momentum across many orders of magnitude in radius, moving from galactic scales down to the disk, and each step can be disrupted by turbulence or star formation. So the mystery is not only the black hole's appetite, but the galaxy's ability to deliver. What kind of host environment keeps a steady inward conveyor belt running, while the nucleus is actively trying to push everything away? This is why TON 618 becomes a psychological pivot in the series. It is not a wall across the sky, but a singularity of influence, a compact object that forces us to confront the universe's ability to concentrate. It also reframes what we mean by largest object. The horizon is not large by cosmic web standards, yet the mass rivals entire galaxy populations, and that mismatch between size and weight is the unsettling part. The black hole's gravity shapes its host galaxy, and the quasar outshines that host by orders of magnitude. The center becomes more visible than the structure around it, like a floodlight that erases the building behind it. In visuals, the host is often reconstructed indirectly, while the quasar saturates the detector. We see diffraction spikes, glare, and careful subtraction, and the audience learns that sometimes the brightest object is also the hardest to separate. Quasars also become tools for mapping the universe, because they can be seen across vast distances. Their spectra carry redshifts that place them in cosmic time, and absorption features reveal the intervening gas between us and them. Even when we do not dwell on those absorption systems, the implication remains. A quasar is a backlight, and the universe between becomes a faint silhouette of hydrogen, metals, and structure along the line of sight. They are not randomly sprinkled, because they trace massive halos and dense environments. Quasar clustering reveals where the early universe built the deepest wells, and where gas supply and dark matter potential aligned to ignite nuclei. That clustering links back to earlier chapters about influence and definition. We used galaxy flows to define basins, and we used clusters to weigh nodes. And now, we read the web through its most extreme central engines. Now, we use quasars as signposts for black holes, and black holes as signposts for rare peaks in the density field. The web appears again, but from the inside out, as if we are tracing the cosmos by its brightest punctures. There is also a caution that echoes our earlier measurement themes. Quasar samples are selection limited, and luminosity biases us toward the most extreme accretors, which can distort our sense of what is typical. Mass estimates depend on calibrations that may shift with redshift and quasar type. The monster label must survive those uncertainties to be meaningful, and the honest approach is to ask how wrong we would need to be. Even with conservative assumptions, TON 618 remains at the far end of known black hole masses. It is a stress test of accretion physics and early structure growth, because it occupies a corner of parameter space where models can crack. The stress test matters because it touches the cosmological principle indirectly. Rare extremes are allowed, but their abundance must match a universe that is mostly uniform, with fluctuations that follow predictable statistics. If too many early monsters exist, then either seeds were larger than expected, growth was faster than expected, or our inferences are systematically biased. Each option has consequences that ripple through galaxy formation and feedback models. If only a few exist, then they become statistical outliers that still demand an explanation. Either way, the existence of even one forces models to account for it, because the tails of distributions are part of the distribution. We can also connect the growth problem to the earlier bulk flow tension. Both are questions about how quickly structure can become extreme under standard assumptions, and both live where cosmic variance and selection effects can mislead. In Shapley, the concern was whether mass concentrations and flows match expected amplitudes. In TON 618, the concern is whether early black holes can reach expected masses, given the limits imposed by radiation and time. Both questions are about the tails of distributions, where the universe tests our confidence. The tails are where selection effects hide, and where new physics might live, because small mismatches are amplified into big surprises. TON 618 also reminds us that black holes are not only sinks. They are engines that light up quasars, and quasars can be used to trace enormous volumes, turning a single compact object into a cosmological marker. When we step back from the single horizon, we see a population pattern. Quasars cluster, and their clustering can outline filaments, nodes, and large-scale alignments, hinting at the scaffolding that fed the earliest giants. In a wide-field visualization, points of light begin to look like constellations. The danger is to see intention in randomness, yet the temptation is real, because the universe does build structure, and it does so with hierarchy. That is the bridge to the next escalation in the documentary. Black holes light up quasars, quasars cluster, and clusters of quasars hint at structures on staggering scales where the map itself begins to feel uneasy. If those quasar groupings are real, they push against the idea that the universe becomes smooth beyond a certain scale. The map begins to look too organized to be random, and we are forced to ask what smooth truly means. So we end this chapter with a paradox that fits the series. The most terrifying size can be a boundary smaller than a star's orbit, holding mass that rivals a galaxy, and doing it while the universe is still learning to build. And when that boundary announces itself as a quasar, it becomes a marker in a bigger pattern. The universe keeps building giants even when the giant is a point, an invisible center that lights the dark. TON 618 ended as a point that lights the dark, and that light becomes a coordinate. On a survey map it is only a dot, but the dot carries a distance, a time, and a physical story. When we plot many quasars together, points start to resemble patterns, threads, knots, and faint alignments that tempt the eye. The question is whether the pattern is a real structure or a trick produced by sparse sampling and sharp definitions. A quasar is a galaxy nucleus in a brief violent feeding phase, powered by a supermassive black hole swallowing gas. As matter spirals inward, it forms an accretion disk that heats to extreme temperatures, radiating from ultraviolet to X-rays. That light is not gentle starlight, it is gravitational energy converted into radiation with startling efficiency. In many cases, the quasar can outshine every star in its host galaxy combined, turning a distant nucleus into a visible beacon. Visually, the host galaxy is often lost, washed out by glare, while the nucleus pins the image like a bright tack. In spectra, broad emission lines rise like ridges, shaped by gas moving thousands of kilometers per second. Those lines are the fingerprints that let surveys recognize quasars across cosmic time, even when the surrounding galaxy is too faint to register. That makes quasars ideal markers for the high redshift universe, where ordinary galaxies fade into noise. Quasars are not sprinkled randomly across space, and that is the first clue that they trace something deeper. They live in massive dark matter halos, where gravity has pulled matter into rare peaks of the cosmic density field. Their environments are biased toward overdense regions, meaning they prefer the high ground of the cosmic landscape. Bias is a technical word with a simple consequence. The tracer exaggerates peaks in the underlying matter field, so clustering looks stronger than it does for average matter. That strength is useful, because it makes faint structure easier to detect at great distances. It is also dangerous because it can make the cosmic web look sharper than it truly is at the same scale. With quasars, we often have bright beacons separated by huge gaps, and the gaps are not empty space so much as unlit territory. The underlying matter can be continuous, while the quasar map looks like a broken constellation. A large quasar group is an inferred association of quasars close in three-dimensional space, assembled from positions and redshifts. It is not a bound object like a cluster, where gravity dominates internal motions and the system has a clear center. It is not a single halo, and it is not a single collapsed structure. It is a statistical structure, defined by a rule for connecting points that may never have interacted directly. The Huge-LQG is the most famous and most disputed of these claims, partly because its scale sounds like a provocation. It was reported as a quasar grouping spanning several billion light-years in comoving scale, a distance that preserves the universe's expansion in the bookkeeping. That number immediately collides with the expectation that the universe becomes homogeneous on large scales, at least in a statistical sense. When a claim arrives with a gigaparsec headline, it presses on a foundational assumption. Cosmologists sometimes call that expectation the end of greatness, a phrase that carries both awe and warning. Beyond a few hundred megaparsecs, fluctuations should average out, and structures should stop looking coherent when you smooth the map. The cosmic web should still exist, but it should blur into a near-uniform background when viewed with a wide enough lens. The Huge-LQG seems to push past that comfort zone, as if the web has drawn a line too long to ignore. To understand the claim, we have to understand the map it came from, and the map is never the sky itself. Quasar catalogues are built from wide surveys that select objects by colour and spectral features, using filters that slice light into broad bands. A quasar's colours shift with redshift, and surveys exploit that shift to separate quasars from stars and galaxies. The catalogue is not a complete census of all quasars, and it never can be, because selection is always a compromise between depth, area, and purity. In the visuals, imagine a mosaic of telescope fields stitched into a footprint, with each tile carrying slightly different noise and depth. Some regions are crisp, others are thinly sampled, and the edges are sharp where the survey stops. Every dot in the catalogue has passed through that pipeline, and every missing dot has a reason that may not be cosmic. When we later infer structure, we are partly reading the universe and partly reading the survey. The original identification used a method called Friends of Friends, a classic tool in cosmology with a deceptively social name. The idea is simple and seductive because it turns geometry into membership. Two quasars are linked if their separation is below a chosen linking length, and the link is treated as a friendship that can propagate. In practice, the algorithm builds a graph, and the graph becomes the object. Once links are allowed, chains can form and chains can grow into something that looks like a continent. A links to B, B links to C, and the group grows even if A and C are far apart. A structure emerges from connectivity, not from a single physical boundary, and that distinction matters. The algorithm does not ask whether the region is dynamically related, only whether it can be traversed by short steps. That linking length is not a minor technical setting, and it is not an afterthought buried in a method section. It is the definition of what counts as connected, translated into a single number. Change it slightly, and the number of groups and their sizes can change dramatically, especially in sparse data. The same sky can produce a handful of modest associations or one sprawling network, depending on that threshold. Friends of Friends works well in dense simulations and in galaxy catalogues with high sampling, where the density field is well traced. With sparse traces, it can stitch across voids by accident, because a few points can bridge large separations. The method can turn a few chance alignments into a giant network, and the network can look persuasive in a plot. The danger is not that the algorithm is wrong, but that it is literal. The Huge-LQG was found in a specific redshift range, where the survey had many quasars, so the point cloud was unusually rich. The group was defined by a linking length chosen to match expected quasar clustering scales, often motivated by correlation functions measured from the same era. That choice is defensible, because it ties the threshold to known clustering behaviour. It is not unique, and the debate begins in that narrow space between defensible and definitive. Redshift is the third coordinate that turns a sky map into a volume, and it is both powerful and fragile. For quasars, redshift comes from broad emission lines that can be shifted by winds and complex gas motions near the black hole. The uncertainty is not only instrumental, it is astrophysical, because the emitting gas is not a quiet clock. Different lines can disagree, and the disagreement can be systematic. Those uncertainties smear positions along the line of sight, stretching points into narrow cigars in moving space. If the linking length is comparable to the smearing, connectivity can be inflated without anyone noticing. A group can look thicker and longer than the underlying distribution, simply because distances are fuzzier in depth than on the sky. In a visualization, the points seem to align into a corridor, but the corridor may be partly measurement blur. Selection effects add another layer of risk, because what you detect is not what exists. Surveys have magnitude limits, so faint quasars at high redshift drop out first, thinning the map with distance. Color cuts can miss quasars with dust reddening or unusual spectra, and some objects fall into the same color space as stars. Even the best selection produces a catalogue shaped by human choices, and those choices imprint patterns. The sky coverage is also uneven, because real observing is constrained by weather, instrument scheduling, and the geometry of the telescope's field. There are edges, holes, and regions of lower completeness where fewer targets were observed or confirmed. A Friends of Friends algorithm does not know why points are missing, and it can misread absence as structure. A gap caused by incomplete spectroscopy can look like a cosmic void. Even the geometry of the survey matters, and this is one of the most unsettling subtleties. A long, thin survey stripe can encourage long, thin groups, because the available volume is shaped like a corridor. If the footprint is narrow, chains are more likely to run along it, and the algorithm will happily follow. The map can whisper wall when it is partly hearing window, so the Huge-LQG becomes a test of methodology as much as a test of cosmology, and that is why it refuses to settle quietly. The reported size is not measured with a ruler on a photograph, and it is not a single diameter you could walk across. It is inferred from a graph of linked points in moving space, where the edges are defined by a threshold. The object is, in a sense, a statement about connectivity. Supporters emphasize that the group is not just one tight knot, and that matters for interpretation. It is an extended association with multiple dense regions connected by the linking rule, like islands joined by shallow bridges. They argue that the density contrast is high enough to be meaningful, and that the configuration is unlikely to arise by pure chance. In their view, the pattern is too organized to dismiss. Skeptics emphasize that meaning depends on the null hypothesis, and that the null is rarely intuitive. If you apply the same algorithm to a random catalogue with the same selection function, you can also get large groups, simply because extremes happen in large samples. The question becomes how often, and under what choices of linking length and redshift uncertainty. A rare headline can be an expected tail. This is where cosmology turns into statistics, and the mood shifts from wonder to discipline. You generate mock catalogues that mimic the survey's footprint and redshift distribution, including the same holes and magnitude limits. You run the same friends of friends procedure with the same linking length, and you count the largest groups. Then you ask whether the observed structure sits comfortably among the largest in the synthetic set. If the Huge-LQG is common in mocks, it is not extraordinary, even if it is visually dramatic. It becomes an expected extreme from a large volume, like the tallest wave in a long storm, rather than a violation of the sea. If it is rare, it becomes a stress test for the model and for the assumptions baked into the pipeline. Either way, the result is a lesson about how we translate points into claims. The key is that rarity must be measured correctly, because a sloppy comparison can manufacture tension. You cannot compare a detected group to a naive random distribution that ignores survey selection, because the survey itself shapes the point cloud. You must compare to the same observational pipeline, including incompleteness and errors, so that the mock has the same blind spots. Only then does rare mean what it sounds like. Simulations add physical realism beyond random catalogues, and they add a deeper question about what the universe tends to produce. In a standard cold, dark matter universe, you can populate halos with quasars using a bias model and a duty cycle, matching observed number densities. The simulation grows structure from early fluctuations, letting filaments and nodes emerge under gravity. Then you ask whether similar groups appear in that synthetic universe when you observe it like a survey. The duty cycle matters because quasars flicker, and the flicker is not a metaphor. A halo can host a quasar only during a short active phase, perhaps tens of millions of years, which is brief compared to cosmic timescales. That means the quasar map is a stroboscopic sampling of the underlying matter field, catching only some peaks while others are dark. The web is continuous, but the lights are intermittent. A stroboscopic map can create apparent gaps and apparent alignments, and both can be misleading. Two halos may be connected by a filament, but only a few of their quasars are turned on at the same epoch. Friends of friends might connect the lit points in ways that overstate the continuity, because it cannot see the unlit halos between them. The algorithm follows the lights, not the mass. Bias also evolves with redshift, and that evolution complicates any fixed intuition about clustering strength. At earlier times, the same quasar luminosity can correspond to different halo masses and environments, because black hole growth and gas supply change with epoch. If the bias is higher, clustering is stronger, and large associations become more likely in the quasar map. A pattern that seems too strong may be partly a property of the tracer, so quasars are special tracers in two opposite ways, and the contradiction is the heart of the puzzle. They reach deep into cosmic time, and they highlight rare peaks where the most massive halos live. They also sample those peaks sparsely, and that sparsity invites overinterpretation when we draw lines between points. The same property that makes them useful makes them treacherous. The Huge-LQG debate, therefore, is not only about one object, and it is not only about one paper. It is about what we mean by an object at all, when the data are discrete and the underlying field is continuous. A quasar group is not a thing you can hold together with gravity. It is a pattern in a point process. The question becomes philosophical as well as statistical. When does a pattern earn a name? This connects back to Shapley and Laniakea, where boundaries depended on definitions rather than walls you could touch. In Laniakea, the definition was dynamical flow, and in Shapley it was overdensity and influence across a region. Here the definition is graph connectivity, a choice that feels objective until you adjust the threshold. Each case reminds us that largest often means largest under this rule. Graph connectivity can be powerful because it turns a cloud of points into a set of components you can compare. It can also be arbitrary because it turns the continuous density field into discrete clusters based on a threshold. The threshold is a human decision, even when guided by theory, and that is why sensitivity tests matter. If the object vanishes when you nudge the rule, the object may be more algorithm than cosmos. To test coherence, researchers look for internal consistency, and they do it in several complementary ways. Does the group persist under reasonable changes in linking length, rather than only at one tuned value? Does it remain when you resample the catalogue or perturb redshifts within uncertainties so that measurement noise cannot create it? Stability under perturbation is a kind of robustness. They also test for anisotropy and elongation, because geometry can reveal algorithmic percolation. A very elongated group can be a sign that the method has begun to chain along the survey volume, rather than isolating a dense region. Percolation is a known phase transition in connectivity problems, where the graph suddenly develops a spanning component. In that regime, group becomes network, and the distinction is not semantic. If you set the linking length too large, the catalogue suddenly becomes one giant group, and that moment can arrive abruptly. The Huge-LQG sits uncomfortably near that regime in some analyses, and that proximity makes the claim sensitive to small choices. A slight increase can merge neighbours, while a slight decrease can fragment the association into smaller pieces. The object can feel both enormous and fragile. Another test is to measure density contrast against the background, rather than focusing on span alone. If the group's quasar density is only slightly higher than average, then its visual impressiveness may come from its size, not its statistical significance. Large volumes can contain mild overdensities, and mild overdensities can look dramatic when outlined by a linking graph. The eye is drawn to the outline, not the contrast. Researchers also compare to alternative clustering methods, partly to escape the chaining behaviour of friends. Minimal spanning trees can quantify connectivity without committing to a single threshold, and Voronoi tessellations can estimate local density with adaptive cells. Kernel density estimators can smooth the field, revealing whether a broad enhancement exists without hard borders. If multiple methods agree, confidence increases, though agreement is never a guarantee. Yet agreement can still be misleading if all methods share the same selection biases, and selection is the quiet villain of many large structure claims. A survey imprint can masquerade as cosmic structure, especially when the footprint is complex and the completeness varies. The only safe comparison is through end-to-end mocks that reproduce the survey, including targeting strategy and redshift errors. Without that, the map can echo the instrument. The controversy sharpened because the Huge-LQG was reported alongside another large quasar group nearby in the sky, and proximity invites narrative. Two large associations in one region can feel like a cosmic wall, a slab of structure stretching across the chart. It can also be a local artifact of sampling, where the survey happened to be richest and the algorithm most eager to connect. When patterns cluster in one area, we must ask whether the sky or the pipeline did the clustering. At stake is not the cosmological principle itself, but our practical use of it in finite data. Homogeneity is statistical, not absolute, and it allows rare extremes in large enough volumes. The real question is whether the reported extremes match the expected tail of the distribution, given the tracer and the method. A universe can be homogeneous and still contain spectacular-looking associations. The end of greatness is often stated as a scale where the universe looks smooth when averaged, but averaging is an operation with choices. It does not forbid large features outright, and it does not demand that every region look the same. It predicts that the contrast of those features should diminish with scale, so that coherence weakens as size grows. The Huge-LQG challenges us to specify what we mean by coherence, so a huge structure can exist, but it should not be too coherent or too overdense when judged against the model's statistics. If a quasar group spans gigaparsecs with strong contrast, it becomes hard to reconcile with standard fluctuations in their growth under gravity. If it spans gigaparsecs with weak contrast, it may be unsurprising, even if it sounds shocking. The tension lives in the combination of span and significance. This is why the word structure is doing so much work and why it feels slippery in narration. In a density field, structure is continuous, with filaments and sheets fading into the mean without sharp edges. In a catalogue, structure becomes discrete, and discreteness tempts us to draw borders and assign names. We are translating a fog into islands, and the translation can invent coastlines. The Huge-LQG sits at the intersection of those two realities, and that intersection is where mystery thrives. The underlying matter field may contain broad, low-contrast features that extend far without becoming a single entity. The quasar catalogues samples that field in a way that can exaggerate connectivity because it highlights peaks and ignores the quieter terrain. The group may be a real enhancement, but its apparent unity may be an artifact. Survey limits make the problem harder because cross-checks become scarce at high redshift. We cannot easily build complete galaxy maps to verify the quasar pattern, and we cannot weigh the region with gravitational lensing at the same fidelity as nearby superclusters. The observational ladder has missing rungs at those distances, leaving inference to carry more weight. That is where careful statistics must replace direct confirmation. We can look for supporting signals, but they are subtle and often noisy at the required scales. Absorption lines in background spectra can trace intervening gas, hinting at extended overdensities along certain sightlines. The integrated Sachs-Wolf effect can hint at large potential wells through correlations with the cosmic microwave background, but the signal is weak and easily swamped. Each supporting test adds context, yet none provides a simple verdict. Even if a large association is real, it may not be a single physical entity with a shared history. It may be a chance alignment of several filaments and nodes that happen to be active in quasars at the same epoch. The map then reflects timing as much as mass, because quasar ignition is episodic and environment dependent. We may be seeing a synchronized flash rather than a monolithic structure. That timing is part of the mystery tone of this chapter, because it shifts the meaning of a map. We are not only mapping space, we are mapping a brief phase of galaxy evolution, when black holes are fed and feedback reshapes their hosts. The universe is being traced by temporary lighthouses, and the lighthouses do not all turn on together. What looks like a wall may be a momentary illumination of a broader landscape. So the Huge-LQG becomes a lesson in humility, and humility is not the same as dismissal. Our biggest claimed objects can be made from a few hundred points, and each point carries redshift uncertainties, selection biases, and algorithmic choices. The group's outline can feel crisp on a plot, yet the underlying reality may be probabilistic and soft-edged. The more dramatic the claim, the more carefully we must audit the steps that produced it. Still, the claim matters because it forces better tests, and better tests improve the entire field. It pushes cosmologists to quantify significance, not just announce size, and to report how results vary with linking length and redshift treatment. It pushes survey teams to model completeness and to publish selection functions, so that others can build faithful mocks. It also encourages transparency about pipelines, because pipelines shape discoveries. It also pushes theorists to ask what the standard model really predicts for extremes, rather than relying on intuition. In a universe with Gaussian initial conditions, rare peaks and long filaments are expected, and their statistics can be computed and simulated. The question is how rare and how connected when you observe them through a biased, flickering tracer. Extremes are where models are tested, but also where misunderstandings multiply. When the tests are done carefully, the tension often softens, though it rarely disappears entirely. Some analyses find that Huge-LQG-like structures can appear in random or simulated catalogues with non-negligible probability, especially when the same selection function is applied. Others find the reported structure is sensitive to the chosen linking length, and that nearby percolation makes the size unstable. The debate becomes less about impossibility and more about interpretation. That does not make the story anticlimactic, because the unease merely changes its source. It makes it more unsettling, because the terror shifts from the object to the inference, and inference is our only tool at these distances. The universe may be smooth, yet our maps can still produce giants, and the giants can look convincing. What else might our methods be quietly assembling? This is the deeper theme of the middle chapters, and it is why the narration lingers on technique. The largest structures are not only out there in the cosmic web, they are also in our methods, in the thresholds and definitions that turn data into entities, and in the human desire to name what we can outline. A catalogue is a powerful abstraction, but abstraction can harden uncertainty into a shape. Yet we should not dismiss the possibility that quasars are revealing real extended overdensities, because the early universe did carry long-range correlations. Inflation imprinted correlations across vast scales, and gravity amplified them into the filamentary network we simulate and observe. Filaments and sheets can extend for hundreds of megaparsecs, and connected complexes can span even more when contrast is low. The question is not whether extension exists, but how we should describe it. If quasars preferentially ignite in connected environments, they can outline those extended features in a way that feels like drawing with fire. The Huge-LQG could be a partial illumination of a real wall or filament complex, with only certain nodes lit at that epoch. It could be a flashlight beam sweeping across the web, revealing some ridges while leaving the valleys dark. In that reading, the structure is real, but our view is incomplete. That possibility keeps the chapter's mystery alive because it preserves two plausible narratives in the same data. One narrative says we found a coherent giant, a feature that stands out even after careful statistical accounting. The other says we found percolation in sparse points, a network assembled by a threshold near a critical regime. Both narratives teach us something, and neither is comforting. So we end by returning to the central question, and by sharpening it rather than resolving it. How can the universe build objects on scales that seem to defy our models? And what do these giants reveal about our limits? Sometimes the limit is not the cosmos, it is the survey, its selection, its geometry, and the algorithms we trust to connect the dots. The next escalation follows naturally because it shifts from flickering traces to denser matter maps. If quasars can appear to line up into immense groups, then galaxies themselves can organize into even larger walls. Those walls are closer to being continuous matter, and they feel like cosmic architecture, not just a graph of points. We leave the quasar map with a final caution, because the biggest patterns can be real, but they can also be the shadows of our definitions. In the next chapter, the dots become denser, and the walls become harder to ignore. We have been climbing through the cosmic web using traces that flicker and fade, and each step has demanded a little more inference. Now we reach a claim that feels less like structure and more like a dare, something so large it tests our willingness to believe maps drawn from sparks. The Hercules, Borealis Great Wall, is reported as an enormous concentration of matter, a suspected overdensity spanning a vast swathe of the sky. It is inferred, not photographed, and its outline is drawn from rare explosions rather than from continuous images of galaxies. On screen, imagine a dark dome of space punctured by a few bright pins, each pin a burst that lived for seconds. The claim places it at high redshift, roughly Z'd about 1.6 to 2.1, where the universe was younger and denser. That corresponds to a look-back time near the universe's middle age, when galaxies were busier and gas was still plentiful. In that era, star formation was nearer its historical peak, and mergers were more frequent than they are today. Redshift is more than a distance tag, because it is also a clock written into light. As space expands, wavelengths stretch, and the spectrum slides toward the red by a factor of 1 plus Z. When we say Z equals 2, we're saying the universe has expanded to roughly 3 times its former size since that light was emitted. In comoving terms, it is said to span on the order of 10 billion light-years, a length that sounds almost like a category error. Even conservative renderings still land in the multi-gigaparsec regime, where our normal intuition about objects starts to break. Visualize a translucent ribbon laid across a star map so long it seems to ignore the curvature of the sky. That number is shocking because it collides with the expectation of large-scale homogeneity, the idea that the universe smooths out when you zoom far enough away. The cosmological principle does not ban structure, but it limits coherence, especially when you ask for a single connected feature. At some scale, the bumps should average down, and the map should stop looking like a landscape. Earlier chapters warned that largest often means largest under this rule, and the rule always matters more than the headline. Here the rule is stranger because the points are not galaxies, clusters, or even quasars in a uniform survey. The wall is traced using gamma-ray bursts, the brightest electromagnetic flashes we know, which arrive like cosmic lightning. They appear without warning, then vanish, leaving coordinates and redshifts as their only durable footprints. The first detection is often a spike in a satellite's gamma-ray counters, followed by an urgent scramble to catch the fading afterglow. In the visuals, the burst is a brief flare, then a dim ember sliding from X-ray to optical to radio. A gamma-ray burst is not one phenomenon but 2 main families, separated by duration and by origin. Long GRBs come from massive star collapse, and short GRBs come from compact mergers, although nature blurs the boundary at the edges. This classification grew out of early catalogues, when astronomers noticed 2 clusters in a plot of burst durations. Long bursts are tied to the deaths of very massive stars and star-forming galaxies, often in regions rich with gas and young stellar populations. Their jets punch outward and briefly outshine the host's entire stellar population, but only for observers aligned with the beam. The core collapses, a black hole or magnetar forms, and a relativistic outflow drills through the dying star's envelope. Short bursts likely come from neutron star mergers, sometimes with a kilonova afterglow powered by freshly synthesized heavy elements. They are rarer in some catalogues, but still visible across great distances, and they connect GRB astronomy to gravitational wave physics. The merger ejector can glow as R-process nuclei decay, a faint but telling signature that follows the gamma flash. In both cases, the key is beaming and energy, because the universe is not giving us a fair sample of explosions in all directions. A narrow relativistic jet concentrates power into our line of sight, so a distant event can still dominate detectors. That also means we only see a fraction of all bursts, because most jets point elsewhere. GRBs are visible across much of the observable universe, because gamma rays cut through dust that would smother optical light. Their afterglows also provide redshifts, anchoring each burst in time, usually through absorption lines imprinted by intervening gas. A spectrum becomes a ruler of sorts, turning a fading point into a measured epoch. That makes them tempting as signposts of structure at redshifts where galaxy surveys thin out, and where ordinary mapping becomes expensive. They can mark overdense regions indirectly, like flares on a dark landscape, hinting at where star formation or mergers are more common. Yet a flare is not a census, and a hint is not a contour. The temptation hides a trap, because GRBs are sparse, and sparsity turns the sky into a canvas for coincidence. A few hundred events spread across the sky can look patterned, even when the underlying field is smooth. Our brains are excellent at finding shapes in scattered points, especially when the shape has a name. The Great Wall claim begins with a clustering signal in GRB positions and redshifts, a bump above what a simple random sky might produce. A subset appears concentrated toward Hercules and Corona Borealis on the sky, and the label follows the constellations rather than any physical boundary. In a sky projection, the patch looks like a bruise of points, darker where several bursts overlap in the same redshift band. The reported feature is not a rigid slab of galaxies, and it is not a photographed filament you can trace with a finger. It is a statistical overdensity in a shell of redshift space, assembled from events within a chosen range. The distance slice acts like a filter, deciding which burst count as near one another in cosmic time. The word wall suggests a continuous sheet, yet the data are discrete points with large gaps, and the gaps are not small. The narration must hold both ideas at once, pattern and uncertainty, without collapsing into certainty. If you zoom in, the supposed wall is mostly empty space, stitched together by inference. To understand the claim, we have to treat GRBs as a biased tracer, in the same way galaxies are biased tracers of dark matter. They do not trace mass uniformly, and they may prefer certain environments, which means their clustering can exaggerate some regions and ignore others. Bias is not a flaw by itself, but it must be modelled. Long GRBs favour low metallicity, massive stars, which are more common in some galaxies and at earlier cosmic times. Metallicity changes stellar winds and angular momentum loss, and those details can influence whether a collapsing star forms the kind of jet we detect. That preference can shift the map away from average matter distribution, emphasizing particular host types. Short GRBs can occur long after star formation because binaries take time to merge, sometimes billions of years. Their host populations differ, which complicates any unified clustering interpretation, and their sky distribution may reflect older stellar mass as much as current gas. Even their offsets from host galaxies can be large, because kicks can send binaries drifting before they collide. Even if GRBs trace star formation traces gas, and gas traces halos imperfectly, especially when feedback reshapes the local environment. Each link adds scatter, and scatter can mimic or erase structure, depending on how the sample is cut. A wall can be strengthened by the right bias, or dissolved by the wrong one. The next issue is exposure, because GRB detectors do not watch the whole sky equally, even when they seem to. Satellites have pointing constraints, Earth blocks part of the sky, and sensitivity varies with background and instrument geometry. Some regions are watched longer, some are watched deeper, and some are watched through noisier conditions. A non-uniform exposure map can create apparent anisotropies, and the effect is easy to underestimate. A region observed more deeply will yield more bursts, and the sky can look clumpy for instrumental reasons rather than cosmic ones. In visuals, an exposure heat map overlaid on burst positions can reveal how structure follows observing time. This is the same lesson as the Huge-LQG, but with higher stakes because the tracer is rarer and the distances are extreme. The rarer the tracer, the easier it is for the survey to become the structure, and the easier it is for a patch of sky to look special. When the data are thin, the observing pipeline becomes part of the universe you are measuring. Small number statistics are the central danger, and they are unforgiving in a way that feels almost personal. If a signal depends on a few dozen events, one reclassification or redshift revision can move the result. A single burst added or removed can change the apparent span by billions of light years. The wall's significance therefore lives inside the details of the test, not inside the drama of the name. We must ask what null hypothesis was used and whether it matches the observing pipeline that produced the catalogue. If the null is too clean, the anomaly will look too sharp. A naive null assumes bursts are isotropic and uniformly sampled, as if the sky were watched with equal patience everywhere. A serious null folds in the detector's exposure, the redshift completeness, and selection thresholds that decide which bursts enter the analysis. It also respects the observed redshift distribution, because the universe is not equally sampled at all epochs. Redshift completeness matters because not every burst gets a measured distance, and missingness is rarely innocent. Afterglows fade, follow-up fails, and the missing redshifts are not random, because brighter afterglows are easier to measure. If a region of sky has better follow-up coverage, it will appear richer in known distance bursts. If redshifts are easier in certain sky regions, or for certain burst brightnesses, the sample becomes sculpted by human and instrumental choices. Sculpted samples produce sculpted structures, and the sculpture can look natural if you forget the chisel. The wall then becomes partly a story about telescopes, not only about cosmology. The clustering metrics also matter because different statistics answer different questions, and they can disagree without anyone making a mistake. Nearest neighbour tests probe local crowding, while correlation functions probe scale dependence across many separations. A method that is sensitive to small-scale clustering can mistake a few close pairs for a large-scale feature. Some analyses use counts in angular cells within a redshift slice, comparing one patch of sky to another. Others use two-point correlation estimators, comparing burst pairs to random catalogues that mimic the survey's selection. In either case, the random catalogue is the silent foundation because it defines what unusual means. Each method needs careful accounting for the sky mask and the redshift distribution, and it must test robustness to how bins are chosen. Without that, a peak can be an artifact of geometry and binning, a ridge created by the grid rather than by the cosmos. Even the choice of coordinate projection can subtly change how clusters look to the eye. There is also the look elsewhere effect, which grows when you scan many redshift slices and many angular partitions, hunting for whatever stands out. If you search long enough, something will look special, and the question becomes how often special appears by chance. The more knobs you turn, the more you must pay for the freedom to turn them. Connecting sparse events can also create walls by construction, because the act of linking is itself a model of reality. If you draw boundaries around the densest patch, the boundary will look coherent even when the interior is thin. A contour drawn around points can feel like a surface, even if it is mostly interpolation. This is the same percolation problem in a new costume, and it has a known kind of drama. With a threshold, separate clumps can be linked into a chain that spans far beyond any single overdensity. The wall can be less a monolith than a network that happens to connect under a chosen rule. A wall can appear when the linking length is near a critical value, where graphs change character abruptly. The graph suddenly grows a giant component, and the headline becomes inevitable, because the largest connected set is now enormous. In visuals, you can watch the network snap together as the linking parameter increases by small steps. So the right question is not only whether bursts cluster, because some clustering is expected in any biased tracer. The right question is whether the clustering implies one coherent feature, or several chance enhancements that our method stitches together. Coherence is a stronger claim than overdensity, and it demands stronger evidence. If the wall were real as a coherent overdensity, it would challenge the end of greatness, the scale where the universe should start to look statistically smooth. It would imply significant structure on scales where fluctuation should average out. The shock is not that matter clumps, but that the clump would remain recognizable across so much volume. Standard cosmology predicts a transition to statistical homogeneity on scales of a few hundred megaparsecs, where density contrasts become small in a relative sense. Gigaparsec coherence is not impossible, but it should be weak, more like a gentle gradient than a wall. The larger the scale, the more the universe's expansion suppresses dramatic contrasts. Inflation sets the initial conditions as near Gaussian fluctuations with a measured power spectrum, and we have mapped that spectrum in exquisite detail in the cosmic microwave background. That spectrum limits the amplitude of very large-scale density variations because long wavelength modes carry only so much power. In plain terms, inflation gives the universe a kind of statistical texture, and the texture is constrained. Gravity then grows structure from those seeds, but growth is scale dependent and time is limited. On the larger scales, expansion and limited time keep contrasts small, so the universe cannot easily build a sharp, contiguous overdensity across gigaparsecs. The biggest modes are still only partly grown, even after billions of years. Simulations of lambda CDM produce filaments and sheets, and they can extend impressively, especially when you view them in thin slices. But the largest coherent overdensities should not dominate a gigaparsec volume, because the mean wins when you average enough space. What looks like a wall in one projection often breaks into separate features in 3 dimensions. If a 10 billion light-year wall were dense and contiguous, it would strain those simulations, not because they forbid large structures, but because they predict how rare and low contrast they should be. It would push us toward either rare cosmic variants or new ingredients, and neither option is comfortable. Cosmic variance is the universe's permission slip for outliers, but even permission has limits. One possibility is that the wall is not a single object but a projection of several structures, aligned by chance in angle and redshift. In redshift space, uncertainties can stack separate regions into one slice, especially when the slice is wide. A broad redshift bin can turn a chain of unrelated overdensities into a single named feature. Another possibility is that the wall is a low contrast feature exaggerated by a biased tracer, where GRBs highlight peaks that are only modestly above the mean. In that case, the wall is partly a translation error, turning a mild enhancement into a dramatic object. The universe could be only slightly lumpy there, while our signposts make it look mountainous. A third possibility is that the sample is too small to stabilize the inference, and the inference is still in its early, fragile phase. A handful of bursts can shift the centroid, the span, and the significance, which means the wall's dimensions may be more elastic than the name suggests. With sparse data, even the direction of elongation can be unstable. Extraordinary scale demands extraordinary scrutiny, because the claim touches a foundational assumption. If homogeneity fails at these scales, many derived inferences must be revisited, from how we interpret clustering to how we estimate cosmic variance. The wall becomes less a curiosity and more a stress test for the framework. The cosmic microwave background already constrains large-scale anisotropy tightly, because it is a snapshot of density and potential fluctuations when the universe was very young. Any giant wall must coexist with those constraints on gravitational potentials, not just on visible matter. A huge overdensity would correspond to a potential well, and potential wells leave fingerprints. Large structures can imprint signals through the integrated sacs, Wolf effect and lensing, subtly shifting CMB photons as they cross evolving gravitational landscapes. But at these distances and contrasts, the expected signals are subtle, close to the noise floor of current maps. The absence of a clear imprint is not a disproof, but it is a reminder of how hard confirmation can be. So the wall is hard to confirm with independent probes, and the difficulty is part of the story. Galaxy surveys at the same redshift are incomplete, and weak lensing maps are noisy at that depth, because background sources are faint and sparse. Even when deep fields exist, they cover small areas, like keyholes cut into a vast door. That leaves us with a methodological tension that fits the series, and it grows sharper the farther we look. The farther we look, the more we rely on rare beacons, and the more our maps become probabilistic rather than photographic. At extreme distance, the universe is not a picture so much as a set of likelihoods. The Hercules, Borealis Great Wall, becomes a looming question mark, hovering between discovery and mirage. It is either the largest known structure, or a pattern assembled by sparse points and imperfect sampling. The unsettling part is that both possibilities can produce a convincing visualization. The responsible stance is not to dismiss it, and not to canonize it, because both reactions are shortcuts. The stance is to treat it as a stress test for how we claim objects at the edge of data, where selection effects are strong. In other words, we test the claim by testing the machinery that produced it. We can ask what future data would change the verdict, and the answer is specific rather than philosophical. More GRBs with uniform sky coverage would reduce noise, and better redshift completeness would reduce sculpting, especially if follow-up becomes more systematic. A larger sample also allows finer redshift slicing, which reduces projection effects, Cross-correlation with galaxy density fields would help, if deep surveys can map the same volume with enough area to matter. If galaxies and GRBs align, the wall gains physical credibility, because two different traces would be pointing to the same underlying structure. If they do not align, the discrepancy becomes a clue about bias or about selection. We can also test the claim in end-to-end simulations, where every step is controlled and therefore interrogable. Populate simulated universes with GRBs using plausible host models, then observe them with a mock satellite that has a realistic exposure map. When the pipeline is simulated, you can see how often it manufactures walls from randomness. If wall-like features appear often under the same pipeline, the claim becomes less revolutionary, because the method is prone to dramatic connected components. If they appear rarely, the claim becomes a sharper anomaly, and the pressure shifts back onto cosmology. Either way, the result is informative because it separates the universe from the instrument. Either outcome teaches the central question in a new way, and it is a question about definitions as much as about matter. The universe may build giants, but our definitions decide when a giant becomes an object, and when it remains a statistical description. At these scales, language can outrun evidence, and names can harden into facts. This chapter also loops back to the bulk flow tension from Shapley, because both stories live at the boundary between expected extremes and claimed exceptions. Both stories ask whether observed outliers match the expected tail of standard cosmology, or whether the tail is heavier than we thought. The difference is the observable. Velocities there, sparse beacons here. In Shapley, the question was gravitational reach and velocity fields, measured through galaxy motions and the dipole-like pull of large concentrations. Here the question is coherence at extreme scale, inferred from sparse traces that blink and disappear. Both cases force us to ask how much of the pattern is cosmic and how much is methodological. In both cases, the danger is the same, even if the data look different on the page. We can mistake a statistical fluctuation or a selection imprint for a physical challenge to the model. The more dramatic the claim, the more we must check the quiet assumptions that sit underneath it. Yet the unease remains, because the claim sits where our intuition is weakest, and where the universe is least forgiving of casual reasoning. A structure that large would not just be a record, it would be a boundary condition, something that shapes how we interpret everything around it. It would imply that some long wavelength mode carried surprising coherence across a huge fraction of the observable volume. If the wall is real, it would constrain inflation-era density fluctuations, because inflation is where the larger scale correlations are set. It would demand that rare, long wavelength modes produce stronger coherence than expected, at least in our patch of the cosmos. That does not automatically break the model, but it would tighten the space of acceptable histories. It would also force us to refine what we mean by homogeneity, a concept that can sound simpler than it is. The universe could be homogeneous in average density, yet still contain rare, haunting superfeatures, like a smooth ocean that still permits occasional towering swells. Homogeneity is statistical, not absolute, and statistics allow surprises. If the wall is not real, the lesson is still unsettling, because it points back at us rather than outward. It means our methods can manufacture colossi from a sparse sky, and the colossi can look persuasive, especially when plotted with confident lines. The mirage would not be a failure of honesty, but a failure of intuition about sparse sampling. So we hold the wall in suspension, as a claim that refuses to settle, neither confirmed nor cleanly dismissed. It is a colossus that should not be there, and that is why it matters, because it exposes the seams between data and narrative. In the visuals, the wall should appear and fade as the selection assumptions change, like a ghost that depends on the lighting. Whether the Great Wall stands or dissolves, the universe undeniably produces giants of another kind, and those giants are not statistical composites, not networks of galaxies across gigaparsecs, but single galaxies swollen into near city-states of stars, each one a dense metropolis of light. After the uncertain outline of a wall, the next giants will be tangible, luminous, and countable. We leave the wall behind with a final rule, spoken slowly because it applies everywhere in this series. The bigger the claim, the more carefully we must audit the pipeline that drew its outline from detection to catalogue to statistic. When the object is made of inference, the inference must be as solid as we can make it. Next, we descend from the largest alleged structures to the largest individual galaxies, where scale shrinks but complexity does not. The strangeness remains, only now it will be concentrated into single systems, not spread across the sky. In that shift, we trade a question mark spanning gigaparsecs for a new kind of wonder, packed into one gravitational island. After walls and maps that may dissolve under scrutiny, we pivot to objects you can point to. Not statistical networks stitched by thresholds, but single galaxies whose scale is written in light. The camera narrows from a web of claims to one luminous body, an island of stars with edges that refuse to sit still. The central question returns with new teeth, because the numbers now have a face. How can the universe build objects that feel too large for their category, yet still fit inside standard cosmic history? When we say too large, are we reacting to physics or to the limits of our definitions? IC 1101 is often introduced as a king among galaxies, an enormous elliptical with a vast stellar envelope. In images, it looks like a pale lantern suspended in a crowded sky, its light thinning outward until it nearly becomes the background. It sits near the centre of a rich cluster, where gravity funnels matter inward for billions of years. Historically, brightest cluster galaxies drew attention because they broke the neat symmetry of galaxy catalogues. Early classification schemes like clean spirals and tidy ellipses, yet cluster centres kept offering something swollen and overgrown. IC 1101 became famous in that tradition, an object that forces astronomers to ask what a galaxy even is. Calling it the largest depends on what we mean by size, and that caveat is part of the story. For galaxies, size can mean a bright core, a half-light radius, or a faint halo traced to a surface brightness limit. Each choice is defensible, yet each choice tells a different tale about formation. The half-light radius, for example, is the radius that encloses half the total emitted light. That sounds objective, but total requires extrapolating the outer profile where measurements become uncertain. In practice, observers fit mathematical curves to the glow, then integrate those curves into darkness. Elliptical galaxies do not end with a sharp edge, and their outskirts fade into the background. The boundary you draw depends on how deep you can see, and how you subtract the glow of the cluster. A tiny error in background estimation can inflate or shrink the apparent halo, especially when the halo is barely brighter than the sky. This is where the visuals become deceptive in a quiet way. A deep exposure reveals a ghostly gradient, and the galaxy seems to spill outward like smoke in still air. In a shallower image, the same object looks compact, even ordinary, as if the king has been disguised. IC 1101's fame comes from its extreme extent in starlight, and its role as a brightest cluster galaxy. BCGs are not typical ellipticals scaled up, because their environment keeps feeding them. They sit where the cluster's gravitational potential is deepest, and where traffic naturally accumulates. A cluster center is a cosmic intersection, where orbits decay and galaxies lose energy. Over time, the central giant grows by hierarchical merging, absorbing companions that drift too close. The process is slow, but it is persistent, and persistence is what builds the largest things. This is cannibalism in the technical sense, driven by dynamical friction in a sea of dark matter. Massive satellites plow through the cluster potential, stir wakes, and slowly spiral toward the core. The wake is a gravitational overdensity, like a drag force made of invisible mass, that steals orbital energy and turns motion into heat. Dynamical friction is easiest to picture as a crowd effect. A moving galaxy tugs on nearby dark matter and stars, creating a trailing overdensity that pulls backward. Over hundreds of millions of years, that gentle pull becomes destiny, and the satellite is delivered to the center. Each merger adds stars, but it also puffs the galaxy outward, especially in its outer halo. Repeated minor mergers are efficient at building size, even when they add modest mass. The reason is geometric. Stars from disrupted satellites are deposited on wide orbits, widening the envelope more than they thicken the core. Major mergers can transform shapes, but minor mergers sculpt the outskirts with particular efficiency. A small galaxy is torn apart before it reaches the center, and its stars are strewn into long tidal streams. Those streams phase mix into a smooth halo, leaving size behind as a permanent signature. The result is a galaxy with a dense central body and an extended diffuse envelope. That envelope can blend into intracluster light. The population of stars no longer bound to any single galaxy. In the deepest images, the boundary between galaxy and cluster becomes a gradient rather than a line. Intra-cluster light is a record of violence that has been stretched thin. Tidal stripping, harassment, and disrupted dwarfs leak stars into the cluster, creating a faint glow between galaxies. The glow is not uniform, and careful observers find arcs, plumes, and asymmetries, fossil imprints of encounters. The physics behind that stripping is straightforward, even if the scene is chaotic. As galaxies pass through the cluster, tidal forces pull harder on their outskirts than on their cores. Stars on the edge are the first to be unbound, and once unbound, they join the cluster's shared stellar sea. This is why IC 1101's size is partly a question about ownership. At what radius do the stars belong to the galaxy, and at what radius do they belong to the cluster? The question sounds philosophical, yet it becomes quantitative when you measure binding energy and orbital distribution. Observers measure profiles and fit models, but the models are not unique. A de Vaucouleurs-like core can sit inside a broader halo, and different decompositions shift the claimed diameter. Some fits use a single Cercic profile, while others add an extra component to represent the intracluster envelope. Those choices matter because the outer light is faint in absolute terms. A surface brightness of 26 or 28 magnitudes per square arc second is not dim like a candle. It is dim like a whisper under a storm. Detecting it requires long exposures, stable detectors, and a ruthless accounting of scattered light. Even the distance matters, because angular size becomes physical size through cosmology. Redshift gives the scale, but the conversion depends on the assumed parameters of expansion. A small shift in the Hubble constant or matter density slightly changes the inferred diameter, and that change rides on top of the measurement uncertainty. There is also the subtlety that the universe is not Euclidean at these distances. Angular diameter distance increases and then decreases with redshift, creating a counterintuitive mapping between angle and size. Cosmology is therefore embedded in every largest claim, even when the object is plainly enormous. Still, the qualitative point holds under any reasonable definition. In a rich cluster center, the biggest galaxy can become an extreme outlier, swollen by time and by traffic. The cluster is a machine that concentrates matter, and the central galaxy is where the machine deposits its winnings. This connects back to earlier chapters about influence and boundaries. Shapley's reach was about gravity across a region, while ICL 1101 is about gravity concentrating growth into one place. One story spans space as a field, while the other compresses that field into a monument. A BCG is a local answer to the same cosmic logic. Matter flows along filaments into clusters, and clusters funnel matter into their central galaxy, building a luminous monument. In simulations, you can watch this happen as a slow rain of sub-halos, each one shedding stars as it falls. The cluster environment also changes how we interpret the galaxy's halo. Hot intracluster gas shines in X-rays, and its brightness can hide faint starlight unless carefully modelled. That gas is not a minor detail, because it contains a significant fraction of the cluster's baryons and shapes the pressure landscape around the galaxy. In X-ray images, the cluster core looks like a glowing fog, brightest where the gas is densest. The optical halo of the BCG sits inside that fog like a pale ember inside a furnace. Separating the two signals is an exercise in patience, and the subtraction itself becomes part of the narrative. Lensing and dynamics remind us that most of the mass is dark matter, not stars. The galaxy's visible radius is not the halo's virial radius, and the two scales should not be confused. A dark matter halo can extend hundreds of kiloparsecs or more, while starlight fades much sooner, unless the environment keeps replenishing it. Gravitational lensing, in particular, offers a reality check that does not depend on starlight. Background galaxies are stretched into arcs, and the pattern of distortion reveals the mass distribution. The lensing mass often extends well beyond the visible envelope, emphasizing that size depends on what component you are measuring. So IC 1101 becomes a lesson in definitions that does not collapse into ambiguity. The galaxy is genuinely huge, but the headline number is a moving target set by thresholds. The thresholds are not arbitrary, yet they are human choices, and the universe does not label its own edges. Its existence does not threaten the cosmological principle the way a gigaparsec wall might. It is a rare extreme produced by common processes given enough time in a dense environment. The cluster center is simply an accelerator for the ordinary rules of hierarchical growth. Yet it still feels unsettling, because it shows how far hierarchical growth can be pushed. If a cluster can inflate one galaxy to this scale, what else can the same engine build? And if the outskirts are built from the debris of many lives, how many histories are hidden in that smooth light? The answer leads to a different kind of size, one that is not a halo radius but a length. A galaxy can become enormous not by starlight alone, but by launching structures far beyond its stars. Here, the scale is not the breadth of a glow, but the reach of a spear. We shift from IC 1101's diffuse envelope to Alcyoneus, the largest radio galaxy yet reported. Its visible starlight is ordinary compared to its radio footprint, which spans intergalactic space. In optical light, it does not announce itself as a titan, yet radio maps reveal a hidden architecture. Radio astronomy has a particular history of surprises, because it sees what the eye cannot. The first radio galaxies were discovered when early surveys found bright radio sources with no obvious optical counterpart. Over time, the mystery resolved into jets and lobes, and a new kind of cosmic scale entered the conversation. A radio galaxy is powered by an active nucleus, where a supermassive black hole accretes matter. Some of that in falling energy is redirected into jets, narrow beams that punch out of the galaxy. The black hole is not a vacuum cleaner in the cartoon sense, but a gravitational engine that converts mass into radiation and motion. Accretion is efficient because it taps gravitational potential energy. As gas spirals inward, it heats to millions of degrees and radiates across the spectrum. A small amount of mass processed near the event horizon can power structures that dwarf the host galaxy. The term giant radio galaxy is defined by extent, usually measured from lobe to lobe. In this category, size means the separation of radio lobes, not the diameter of the stellar body. The lobes are the terminal reservoirs, the places where the jet's energy is stored and slowly released. Alcyoneus is extreme because its lobes reach millions of light years across. It turns one galaxy into a phenomenon that competes with clusters in scale, at least along one dimension. The name evokes a mythic giant, and the measurement justifies the poetry. To make this accessible, we slow down the engine room without losing the mystery. Gas falls toward the black hole, forms a disk, and heats, as friction and turbulence move angular momentum outward. The disk is not a solid object, but a rotating plasma where magnetic stresses act like a kind of viscosity. Near the center, magnetic fields are twisted by rotation and by the flow of plasma. Those fields can tap the black hole's spin or the disk's energy and channel power into jets. In the language of physics, electromagnetic fields can carry energy and angular momentum away, allowing matter to fall inward while launching a collimated outflow. The jets are not streams of normal gas moving gently through space. They carry relativistic particles and magnetic fields, and they remain collimated over distances that seem impossible. Collimation is maintained by pressure gradients and magnetic hoop stresses, which pinch the flow into a narrow channel. Relativistic means the particles move close to the speed of light, so their behavior is shaped by special relativity. Their lifetimes depend on how quickly they lose energy, and those losses depend on magnetic field strength and radiation fields. In other words, the jet's brightness is a clock, and the lobe spectrum is a record of aging. As the jets plow into the surrounding medium, they terminate in shocks and inflate lobes. The lobes are reservoirs of energetic electrons, and they glow by synchrotron radiation. At the termination points, called hotspots in many sources, kinetic energy is converted into particle acceleration and heat. Synchrotron emission is light from charged particles spiraling in magnetic fields. It is strongest at radio wavelengths for the energies and fields typical of these lobes. The spectrum often follows a power law, and its curvature can reveal how long the electrons have been radiating since their last acceleration. Radio maps reveal what optical images cannot, because the lobes are not made of stars. They are bubbles of plasma and magnetic structure, visible because they radiate as they age. In a composite view, the optical galaxy sits like a seed, while the radio lobes bloom outward into a structure that feels almost architectural. The environment matters as much as the engine, and this links back to clusters again. A low-density intergalactic medium offers less resistance, letting jets propagate farther before fading. Resistance here is not friction in the everyday sense, but ram pressure and entrainment that can disrupt the flow. That helps explain why the largest radio galaxies often live in quieter surroundings. In a dense cluster core, jets can be bent, disrupted, or confined, limiting their final size. The classic bent, head-tail radio galaxies show this clearly, with jets swept back by motion through dense intracluster gas. Alcyoneus suggests a combination of sustained activity and favourable conditions. The black hole must deliver power for long enough, and the surrounding medium must allow expansion. It is a partnership between a compact engine and a permissive cosmos, and either one can set the limit. Time is part of the scale, because lobes grow over tens to hundreds of millions of years. A giant radio galaxy is not a single explosion, but a long campaign of energy injection. If the engine flickers on and off, the lobes can show layered structures, like growth rings written in radio light. Even after the central engine dims, the lobes can persist as ghostly structures. The particles cool, but the bubbles remain as cavities and relics, slowly mixing with their surroundings. The radio brightness fades first at higher frequencies, because the highest energy electrons lose energy fastest. This echoes the Phoenix cluster story, where jets carve X-ray cavities in hot gas. The same physics appears again, but now the cavities are stretched to intergalactic proportions. In both cases, the jet does not merely shine, it rearranges the medium, leaving depressions, shocks, and ripples that can be measured. The jets also carry feedback, which can regulate star formation by heating or expelling gas. A galaxy can limit its own growth even as it projects energy far beyond its visible edge. Feedback is one of the reasons massive galaxies stop forming stars efficiently, turning red and quiet while their black holes remain capable of violence. That feedback loop ties the smallest and largest scales together in one mechanism. A black hole smaller than the solar system can shape structures millions of light years long. The contrast is not rhetorical. It is a literal ratio of scales that nature somehow bridges. Here the central question sharpens into a paradox that feels almost like horror. The universe builds giants by letting tiny engines run, and by letting environments amplify their reach. The dread comes from the calmness of it, because nothing supernatural is required, only time and physics. We also return to the theme of measurement, because radio size is not a simple diameter either. The lobe edge depends on sensitivity, frequency, and how you define the contour of emission. A contour drawn at 3 times the noise level will differ from one drawn at 5, and the difference can be hundreds of kiloparsecs. Low-frequency surveys reveal older electrons and larger extents, while higher frequencies can miss the faint outskirts. The largest objects are often found when instruments finally become sensitive to the dimmest edges. In practice, new surveys do not merely add objects, they extend the universe's apparent inventory of extremes. Projection adds another uncertainty, because we see a 2-dimensional sky. If a jet is tilted toward us, its true length can differ from the apparent separation of its lobes. The effect is geometric and simple, yet it can complicate catalogue rankings, especially when the sample includes many orientations. Even with these caveats, Alcyoneus remains a legitimate extreme in the catalogue. It is not a percolation artifact, because the lobes are contiguous emission tied to one nucleus. The morphology connects back to the host, and the symmetry of the lobes supports a single central engine. IC 1101 and Alcyoneus therefore represent 2 ways galaxies become enormous. One grows by mergers and diffuse halos in cluster centers, and the other grows by jets that extend far beyond stars. One is built by accumulation, while the other is built by projection, mass gathered inward versus energy flung outward. Both stories depend on environment, which is the deeper continuity of this chapter. Clusters feed central galaxies, and the cosmic medium shapes how far jets can travel. The same universe that concentrates matter into nodes also provides the low-density corridors that let jets run for millions of light years. Both stories also deepen the series' tension between object and definition. The giants are real, but the numbers we quote depend on thresholds, sensitivity, and where we draw edges. That dependence is not a weakness of science, but a reminder that nature often hides its most dramatic structures at low contrast. That tension is not a flaw, it is a clue about how the universe hides its extremes. The largest structures often live at low contrast, where discovery requires careful subtraction and patient instruments. We are not only measuring the universe, we are learning how to see it without being fooled by our own glare. We end with a pivot in geometry, because these giants express size as breadth and length. Halos spread outward, and jets spear across space, but the universe also draws circles. Sometimes the cosmos outlines its scale with curves, with arcs and rings that appear briefly and then vanish. Jets and galaxies show size in one dimension, measured as radius or span across lobes. Next, the cosmos sketches rings and arcs in fire, transient patterns that outline vast structure across the sky. We have chased giants made of galaxies and giants made of jets, then giants made of inference. Now the universe tempts us with a shape that feels deliberate, almost accusatory. A ring. The giant GRB ring was reported as an unusual arrangement of gamma-ray bursts on the sky. It appears as an arc or near circle when plotted in angular coordinates and redshift, like embers outlining a rim. The claim is not about one explosion, but about many brief beacons forming a single outline. In the visualizations that made the story travel, the points do not fill a region. They seem to trace a boundary, leaving a quieter interior that reads as a whole. Our eyes are trained to treat circles as messages, even when the universe never meant to write one. The reported distance places it at cosmological redshift, roughly around Z near 0.8 in many summaries. That corresponds to several billion years of look-back time, when star formation and mergers were still more active. The ring is drawn from events that last seconds, yet it hints at a structure lasting eons. At that epoch, the universe was smaller in proper size, and galaxies were building heavy elements rapidly. Massive stars lived fast, died young, and seeded their surroundings with metals and dust. If GRBs are signposts of those deaths, then each burst is also a timestamp, an instant pinned to a long cosmic era. Its implied scale is the shock. Depending on assumptions, the diameter is quoted in the multi-gigaparsec range, on the order of several billion light-years. That is large enough to collide with the end-of-greatness intuition, where homogeneity should start winning. That intuition is not a vague aesthetic preference. In standard cosmology, the density field becomes smoother when you average over larger volumes, because fluctuations cancel statistically. The cosmic web persists, but its contrast should fade when you zoom out far enough. A wall can be dismissed as a chain stitched by thresholds, because walls are easy to imagine as percolation. A ring is harder to shrug off, because rings feel like geometry with intent. The mind reads a circle as a boundary, even when the data are only points. There is also a psychological asymmetry in the shapes we trust. A line can be an accident of sampling, and a cluster can be a coincidence of attention. A circle, however, implies a center, and a center suggests a cause. Gamma-ray bursts make this possible because they are visible across enormous distances. They punch through dust and can be detected when ordinary galaxies are too faint for wide mapping. Each burst becomes a coordinate and a redshift, a dot pinned to cosmic time. A GRB begins as a flash of high-energy photons, often from a relativistic jet powered by a collapsing massive star. The gamma rays arrive first, but they do not carry a precise address. The afterglow, X-ray, optical radio, lets astronomers refine the position and identify a host galaxy. Redshift enters through that afterglow or the host spectrum, where absorption and emission lines slide to longer wavelengths. It is a simple measurement in principle, yet it is fragile in practice. The afterglow fades quickly, and the window for spectroscopy can close within hours. But GRBs are also the most dangerous kind of tracer for pattern claims. They are rare, beamed, and discovered by instruments with uneven sky exposure. A sparse set of dots can look like a symbol, even when the underlying field is bland. Beaming matters because we do not see most bursts at all. We see the few whose jets happen to point toward Earth, which turns the observed distribution into a filtered version of reality. That filter is not uniform across the sky or across cosmic time. The ring claim therefore lands exactly on the documentary's central question. How can the universe build objects on scales that seem to defy our models of structure? Or are we watching our own pattern-making instincts collide with limited data? To evaluate the ring, cosmologists start with a blunt distinction. Is the ring a physical object in 3 dimensions, or a projection artifact on a 2-dimensional sky? The sky is a dome of directions, not a map of depth. A ring on the sky can come from several very different 3D realities. It could be a shell, where bursts lie on the surface of a roughly spherical overdensity. It could be a torus, a donut-like distribution with a real hole through the middle. It could also be an arc cut from a filament or wall, where only part of a larger structure is sampled. It could be a chance alignment, where unrelated clumps happen to sit at similar redshift. The same 2D picture can hide multiple 3D stories. Projection is the first trap because we observe angles more easily than distances. Even when a redshift is measured, it is not a direct ruler without cosmological assumptions. A thin redshift slice can still include a thick chunk of co-moving space. Redshift is not just distance, and it is not just velocity. It is a record of expansion, which means converting z into a co-moving coordinate depends on parameters like h0 and the matter density. The conversion is well constrained, yet it's still a model-dependent translation. If you take a 3D cloud of points and slice it, the slice can look like a ring. A spherical shell intersected by a plane becomes a circle, even if the shell is not special. A curved filament can look like an arc when viewed from the right angle. The geometry is simple, but the consequences are not. A shell is a surface in 3D, while a ring is a curve in 2D. Confusing them is easy when the data are sparse and the bins are wide. There is also a subtlety about thickness. A real shell would have depth, because no physical process draws an infinitely thin surface in space. If the claimed ring is thinner than the expected uncertainties, that mismatch becomes a warning light. Cosmologists therefore ask what ring means operationally. Is it a set of bursts with similar redshift that cluster in angle around a centre? Or is it a visual impression created by plotting choices and human attention? A torus is the most provocative interpretation, because it suggests a coherent, non-trivial topology in matter distribution. A shell is less exotic, because shells can arise from statistical features in the density field. A chance alignment is the most mundane, but it can be the most likely. The history of large-scale structure claims adds weight to that caution. From early pencil beam surveys to the first wide maps of galaxies, cosmology has repeatedly watched patterns appear, fade, and reappear with better data. The lesson is not cynicism, it is calibration. To decide, we need to talk about how GRBs are localized and selected. A burst is first detected in gamma rays, often with coarse positional accuracy. The afterglow follow-up improves the position, but not every burst gets that treatment. Localization uncertainties smear points on the sky. A few degrees of error can move a burst across the apparent ring boundary. Even arc-minute errors matter when you are testing a thin curve against a random sky. The uncertainty is not merely a circle around a point. It can be elongated, instrument-dependent, and correlated with brightness, which means the best localized bursts are not a random subset. When a pattern uses only bursts with redshifts, it inherits that bias automatically. Redshift uncertainties and incompleteness add another layer. Many bursts never get a redshift because the afterglow fades or the host is too dim. The missingness is not random, because brighter afterglows are easier to measure. Even when a redshift is obtained, it may come from different features with different reliability. Some are measured from host emission lines, others from absorption in the afterglow spectrum. A few are photometric estimates, which are useful but broader and easier to misbin. Selection biases can sculpt patterns. Long GRBs prefer low metallicity environments and trace star formation in a biased way. Short GRBs trace older stellar populations and can occur far from their hosts. That astrophysical preference matters because it changes what overdensity means. A region rich in star formation could produce more long bursts without being dramatically richer in total mass. The tracer is not lying, but it is speaking a dialect. A mixed catalogue is therefore not a clean tracer of mass. It is a tracer of detectability, beaming, follow-up success, and astrophysical preference. Any pattern must be tested against that full pipeline, not against an idealized isotropic universe. Detector exposure maps matter as much as cosmology. Satellites do not watch the sky uniformly because of pointing constraints and Earth blockage. Sensitivity varies with background, instrument geometry, and mission history. A spacecraft spends more time looking away from the Sun, and it avoids regions where the Earth's limb brightens the gamma-ray background. Over years, those choices accumulate into a patchwork of deeper and shallower coverage. The sky, in other words, is not observed with equal patience. If one region of sky has deeper exposure, it will yield more bursts. If one region has better optical follow-up coverage, it will yield more redshifts. A ring can be drawn by where we looked, not by what exists. Ground-based follow-up adds its own geography. Weather, telescope time, and the distribution of observatories across latitudes all shape which afterglows get spectra. The catalogue becomes a collaboration between the cosmos and the logistics of night. Sample size is the central pressure point. A ring claim often rests on a few dozen events in a chosen redshift interval. In that regime, the difference between anomaly and coincidence can be one burst. Statistics behave differently when the data are sparse. The probability of an apparent pattern is not intuitive, because the number of possible patterns is huge. If you search many redshift slices and many centers, something will look ring-like. This is the look elsewhere effect in its most seductive form. You do not need to cheat to find a circle. You only need enough ways to draw circles, and the human brain supplies those ways effortlessly. We try different map projections, different smoothing kernels, different color scales, and different cuts in redshift. Each choice is reasonable, yet the space of choices becomes a silent multiplier of false surprise. Cosmologists therefore build null tests that mimic the survey. They generate random catalogues with the same sky mask and exposure map. They match the observed redshift distribution and the probability of getting a redshift at all. Then they ask a specific question. How often does a random catalogue produce a ring of similar strength under the same detection and selection rules? If the answer is often, the ring is a mirage. The choice of statistic matters, because different tests reward different shapes. Nearest neighbour methods emphasise local crowding and can highlight arcs. Two-point correlation functions average over angles and can dilute a ring into a mild bump. Some analyses use counts in cells on the sky within a redshift slice. Others fit circles or arcs and measure how tightly points hug the curve. Each method has a failure mode that can turn noise into structure. A circle-fitting algorithm can also create confidence by construction. If you ask a method to find the best circle, it will always find one, even in random points. The real question is whether the best circle is unusually good compared with the null. Binning is a quiet source of drama. A redshift slice that is slightly wider can merge separate clumps into one ring. A slice that is slightly narrower can break the ring into fragments and erase the headline. Even the definition of distance matters, because comoving and proper scales differ. At these redshifts, a gigaparsec today was smaller in proper size when the light was emitted. The ring's size depends on which cosmic ruler you choose, so the ring becomes a test of our entire mapping philosophy. Are we seeing an object, or are we seeing the intersection of a 3D distribution with our 2D sky and our 1D redshift bins? The universe may be smooth, while our slicing makes it look scarred. Yet the possibility that it is real cannot be dismissed without care. If a ring-like overdensity exists on multi-gigaparsec scales, it would be among the largest coherent features ever proposed. It would sit in the same uncomfortable category as the Great Wall claims, but with a more specific geometry. If real, what could cause it? The first option is a large-scale density feature in the cosmic web, a region where matter is slightly enhanced in a broad shell. In that case, the ring is not a sharp boundary, but a low-contrast ripple. In simulations of LCDM, the largest features are not rigid objects. They are regions where filaments and nodes happen to align, where the density is a little higher across a wide volume. A ring could be the contour line of that gentle hill traced by a biased tracer. Large-scale ripples do exist in standard cosmology, but they are statistical. Baryon acoustic oscillations imprint a preferred scale in the clustering of galaxies. They are a remnant of sound waves in the early plasma, frozen into the matter distribution. In the first few 100,000 years, photons and baryons were tightly coupled, and pressure supported oscillations like a cosmic drumhead. When the universe cooled enough for atoms to form, the photons decoupled and streamed away. The wavefront, however, left a faint imprint in matter. BAO is often described as a ring in correlation space, because it appears as an excess probability at a characteristic separation. But BAO is not a single ring you can point to on the sky. It is a subtle bump revealed only by averaging over many galaxies. That distinction is crucial. BAO is around 150 megaparsecs in comoving scale, far smaller than a multi-gigaparsec ring claim. BAO is also a statistical feature, not a unique structure with a center. So invoking BAO-like physics for the giant GRB ring is tempting but risky. It can explain why the universe likes preferred separations, but it does not naturally produce one enormous ring traced by a few dozen bursts. The scale mismatch forces caution. Another physical option is cosmic variance amplified by bias. GRBs are biased tracers, so they can overrepresent rare peaks in star formation. A modest overdensity in matter could become a strong overdensity in GRB counts. Bias is a technical word with a plain meaning. The tracer does not sample matter proportionally. If GRBs prefer certain environments, then the contrast in their distribution can exceed the contrast in the underlying density field. A small hill in matter can look like a mountain in bursts. In that scenario, the ring is not a new kind of object. It is a normal fluctuation seen through a magnifying glass made of selection and astrophysics. The universe remains statistically homogeneous, but our tracer exaggerates the contrast. A third option is that the ring is not physical at all, but systematic. Exposure anisotropy could create an apparent arc. Follow-up strategies could cluster redshift measurements in certain regions. Systematics can also hide in catalogue assembly. Different missions have different sensitivities and localization methods. Combining catalogues can introduce seams, where one region of parameter space is sampled differently than another. Even the classification of bursts can matter. If some bursts are misclassified between long and short, the inferred host population changes. That can shift the expected clustering signal and alter the null model. If the ring were confirmed as a genuine overdensity, it would pressure test the cosmological principle in a specific way. Homogeneity is statistical, but it predicts that extreme coherent features become very rare beyond a few hundred megaparsecs. A multi-gigaparsec ring would live far out on that tail. That would not automatically break LCDM, because rare things can happen in a large universe, but it would force us to quantify rarity with honest selection functions and honest trials factors. The anomaly would need to survive the full accounting. It would also demand independent confirmation from other tracers. Galaxy surveys in the same redshift range could test for a matching overdensity, though wide area depth is hard. Weak lensing could test mass directly, though signal to noise at that distance is punishing. Cross-correlation is the cleanest path. If GRBs trace a real density feature, galaxies should show some corresponding enhancement. If galaxies do not, the ring may be a tracer artifact or a statistical coincidence. This is where the chapter's mystery becomes the climax. The ring sits at the boundary between pattern and proof, where our tools are powerful but incomplete. It is a cosmic halo of fire that might be a scar, or might be a trick of perspective. Imagine the sky map in silence, a dark dome sprinkled with markers. Now imagine the same map with the exposure heat map beneath it, bright where the satellite lingered and dim where it rarely looked. How much of the ring survives when you see the observing strategy as part of the picture? The deeper lesson is that the universe loves to tempt us with shapes. We see lines in walls, circles in rings, and faces in the noise. Cosmology has to be a discipline of resisting the first story the map suggests. Earlier chapters warned that percolation can turn sparse points into walls. The ring is the same warning, but sharper, because a circle feels like a verdict. The danger is not only that we find patterns, but that patterns find us. So we return to the central question with a colder edge. How can the universe build objects that seem too large for the model? Or how can our limited view build objects that seem too large for the universe? The giant GRB ring forces a final humility about geometry. We do not observe the universe as a 3D volume. We observe it along a light cone, where distance and time are fused. Every map is therefore a projection through time. A ring at one redshift is not a ring now, because now does not exist for that structure in the same way. We are stitching together different cosmic ages into one picture. That stitchwork is easy to forget because the plot looks static, yet each point is a different moment in the universe's history, separated by millions of years of cosmic evolution. The ring, if it exists, is not a snapshot, it is a montage. That is the boundary condition hiding inside the ring story. The largest objects in our catalogue are often not objects at all, but features on our past light cone. They are patterns in what we can see, not necessarily structures we could traverse. After walls, groups, and rings, we reach the ultimate limit. The limit is not a wall of matter, but a horizon of information. It is the edge set by light travel time and cosmic expansion. The next chapter confronts that horizon directly. The universe's edge is not a place you could fly to. It is a boundary in time, where the observable ends and the unknown begins. The ring fades into that realization. Even if the circle is real, it is drawn on the surface of what we can observe. Beyond it lies not emptiness, but unmeasured cosmos, forever outside our light. And that is the final twist the universe offers. the largest structure may be the one we never meant to name, the boundary of observation itself, a limit that turns every giant into a question about what seeing means. We end at the largest object we can define, the observable universe itself. It is not a wall in space, but a limit in time, set by how far light has travelled since the hot, bright beginning. Its particle horizon marks that travel limit, so today's radius is about 46 billion light-years, not 13.8. The number grows because space itself has been expanding while the photons were in flight, like ink dots drifting apart on a stretching sheet. Space expands metrically, which means the cosmic ruler changes, stretching wavelengths into redshift as photons cross ever-growing distances. In that picture, some galaxies recede faster than light, yet relativity stays intact because no one locally outruns a nearby beam. Astronomers once argued over whether such horizons were real boundaries or bookkeeping tricks, but precision cosmology has made them measurable. Beyond lies an event horizon, where dark energy ensures future signals never reach us. Over billions of years, more galaxies slip past that line, fading from possibility into permanent silence. This reframes debated giants, since sparse traces and thresholds can mimic rare extremes in a mostly homogeneous cosmos. Euclid, Rubin, and SKA will test those tales with deeper, cleaner maps, turning hints into statistics. The terror is not size alone, but horizons that bound what physics can ever verify, even as our instruments sharpen at the edge. Across this journey, scale stopped being a number and became a method, because every rung upward changed what size even meant. We learned to measure with light years and redshift, to separate proper from comoving distance, and to treat every catalogue as a translation of the sky. In our own neighbourhood, Laniakea taught us that some of the biggest objects are really flow patterns, gravitational watersheds traced by peculiar velocities rather than bright galaxy chains. Shapley pushed that lesson outward, a dense knot whose influence fades without a clean border, and whose pull on our motion still depends on how we weigh mass through lenses, X-rays, and velocities. Phoenix reminded us that even when an object is undeniably real and bound, its heart can still break expectations. Where cooling gas, starbursts, and black hole feedback argue about control, TON 618 shrank the stage to a solar system, sized event horizon, yet reopened the growth problem, showing how the most compact giants can be the hardest to explain. Then the map began to flicker as Huge-LQGs, GRB walls and rings rose from sparse traces, and the story turned into a trial of definitions, algorithms, and selection effects. By the time we reached the observable universe itself, the largest thing became a boundary drawn by light and time, not a wall in space, and the true constraint was what information can ever reach us. The through line is unsettling and beautiful, a cosmos that is statistically smooth on the largest averages, yet still capable of rare extremes that feel like scars. Some giants, like clusters, galaxies, and radio jets, are physical systems with engines and thermodynamics, while others, like walls and rings, may be the shadows cast by incomplete sampling on a growing light cone. That distinction does not cheapen the mystery, it sharpens it, because the universe is not only building structures, it is also challenging us to define what counts as a structure. In the end, largest is never just a record, it is a stress test, and every stress test forces our models to declare what they truly predict. If Shapley's reach, or a quasar chain's apparent span, seems to strain LCDM, the most honest response is not to choose wonder over rigour, but to let better data decide which feeling survives. Euclid, Rubin, and the SKA will not just add points to the map, they will expose the map's biases, showing whether the biggest claims are coherent entities, overlapping regions of influence, or statistical mirages made persuasive by our hunger to connect dots. So what breaks first when the universe draws something too large to believe? Our maps, our theories, or the idea of any limit at all? The answer is that the limit was never a cosmic fence, it was our past light cone, and what breaks most often is our intuition, followed closely by our definitions of connectedness. Theories do bend under pressure, but they bend in specific, testable ways, and the giants are the instruments that reveal where the framework is stiff and where it is flexible. If the Hercules, Borealis Great Wall, the Huge-LQG, or the giant GRB ring endure after end-to-end mocks, exposure maps, and cross-correlations, then they become real anomalies to explain within a nearly homogeneous universe. If they dissolve under better accounting, they still teach the same lesson, that the cosmos can look haunted when we sample it with rare biased beacons. Either way, the opening question changes shape, because the universe is not only asking how big it can build, it is asking how carefully we can measure without mistaking a pattern for a thing. And the closer we get to the horizon, the more every object becomes a blend of geometry, time, and probability, stitched together by the way light arrives. In the end, the most terrifying size is not a wall of galaxies, or a jet spanning millions of light years, but a boundary where the universe turns into history. Beyond that horizon may be more matter, more structures, even more laws, yet they remain forever untested, not because space ends, but because time does. The giants we can see are therefore both monuments and warnings, telling us that a mostly uniform cosmos still permits rare, haunting extremes, and that our greatest discoveries will always be shaped by what the universe allows us to know. If there is a final scar written across the sky, it is this, the edge of information, where the map becomes a memory and the unknown is not empty, only unreachable. As new surveys redraw the cosmic web, follow the evidence with patience, and ask which giants remain when the selection effects are finally stripped away.